Welcome, everyone. This is Michael Gibbs, and I'm the founder and CEO of Go Cloud Architects and Go Cloud Careers. And I'm super excited to be here with you on day 7 of the free Cisco Certified Network Associate Bootcamp. Again, this is a completely free CCNA 200-301 program, so you can pass the Cisco Certified Network Associate exam. My name is Michael Gibbs, and I've been working in technology for over 25 years. I'm one of the original Cisco certified internet experts. My CCIE number is 7417. I've spent about a decade with Cisco, and I've been in technology, specifically networking, for over 25 years, and I absolutely love it. So in this course, we're going to talk about the CCNA, which is obviously the Cisco CCNA 200-301 exam. We'll be talking about Cisco networking essentials, and whether you call this network administrator training or network engineer training or cloud architect training, it's essential for any of you in these roles. So I like to view this as networking for cloud computing, and I like to view this as cloud computing technicals. But the reality is, whether you're a network engineer or a cloud architect, you're still dealing with networking. And what is the cloud? It's a network in a data center that's been virtualized. So the Cisco CCNA course or the CCNA course for beginners or this free network training will help you as a cloud architect, a solution architect, a network engineer, an enterprise architect, or even a network admin. And that's why we're teaching these things. So we've obviously covered everything from what is a computer network and an intro to networking course to networking and cloud computing. And we're going to have lots of fun with this free CCNA training. So let me know you're all there by typing hashtag CCNA in the chat box. And we know that you're going to be there. So keep all these things. We're super excited to have you back. So let's just talk about a few things. Make sure you all know to download your completely free version of our AWS Certified Solution Architect Professional book. Definitely want you to see this book for the following reason. It covers everything from the beginning foundational stage of the cloud all the way to passing that AWS Certified Solution Architect Professional exam. It's a completely free book. And not only is it a completely free book, it will help you get your first cloud architect job, learn the cloud. And I really want the best cloud architect careers for you. So I just wanted to let you know that. Also, if you're working for cloud computing, on our channel, and Chris will provide links to it, we have a completely free AWS Certified Solution Architect Associate course. And even though it's super basic compared to this, we also have an AWS Advanced Networking course. And that is, again, completely free. And we're out there to guide you to build your best career. We have multiple free events per month, for example, or free events per week where you come on our channel and we'll answer any questions you have. You can see us on YouTube. We've got thousands of videos for you. And guess what? You can see us in the press almost every day of the week. We're out there to help you build your best career. Today, as a matter of fact, we were featured in a magazine that only interviews CEOs. And they interviewed us and was talking about how to help people get their first cloud architect jobs, how to leverage the Great Resignation, how to keep employees' best talent. And I got to tell you, it's going to help you get hired. So I'm going to pop a link to that article. We posted it on LinkedIn this morning. So you can go out there and grab it if you desire, because I want you to have, by far, the best cloud architect careers. And there's a lot of information in this free article that you can receive that's in the chat box to help you go out there and get cloud architect hired. Build your network engineering career, build your network architect career, just have a better career in general. So go out there, check that article out. It even links back to our YouTube channel. So there's lots of cool things that you can learn about the future work and how to get that first job. So let's go back and we'll start talking about networking, because, networking is really, where it's at. Without the network, we've got nothing working. So let's talk about some networking things. Yesterday, we worked on some routing, we worked on some access. Let's talk about securing network devices now. So how do you secure them? So here's the thing. Do you see how every time so far, we've actually put a password directly on the device? Password, Cisco. We put the password on the device. Did you notice that every time I did a show run, you could actually see the password? And then I entered the service password encryption command, and guess what? Then it was an encrypted password. But guess what? The password's still stored on the router. Does this seem like a good idea? Hack into the router, hack into the passwords. No. So if we want to make our devices secure, it's better to take the authentication or authorization and accounting and put it somewhere else. Okay, let's kind of think about that and keep that in our mind. How would we do that? Well, if we were to telnet our SSH to a router, and then the router would go ask somebody else, like a radio server, is Mike Gibbs allowed onto the network? Yes, he is. What is Mike Gibbs allowed to do? He can do anything he wants. Okay, that's it. So when we're dealing with securing these things, one of the things is just to secure the passwords. And let's face it, if you keep your passwords on an encrypted radio server, or your passwords are stored in an Active Directory server, you don't have to put it in the router. So that's a lot more efficient. Much, much, much more efficient. So, if you're doing it on the router, guess what? We can still do it by place the passwords in certain places, but if we can take it off, we can. But even on the router, we still want to encrypt the passwords. So I know I showed you this before. Let me make sure that I still have it up and running. I'll show you one more time. Let's go back to one of our servers. We just did an OSPF lab. We'll open it up. I just want to show you what we did yesterday, and I want to show you what I mean by the passwords being clear text and the passwords being not clear text. So let's go back to our server. Let's go to this device. It's never been here. We've not used it for anything. No, we don't want to configure this dialog box. I'm just going to show you what I mean by passwords and securing these passwords. Now, the reality is, for the most part, you're going to use a TACAX or a radio server or an Active Directory server, but, let's just walk through it. So in this particular environment, we got our device. Configure this. Big terminal. Let's say password. Cisco. But now when we do this, let's see. Oh, wait. You can actually see the root password by looking at this. That's not so good. Let's fix that. Now look at that. All I did is I typed service password encryption, and now there's my new password. So that's really what we were trying to show you. That's how you make it a little more secure. Even better, don't store it here anywhere, store it in a radio server. So just kind of keep that, and we can do that anywhere we desire. Let me just make sure this is shut off. Apologies. Okay, so now you know what we're dealing with regards to that. So let's make sure we give you stuff that are. So we also have the ability to just set it up as an enable secret with an MD5 hash. So let me show you another way that we can do this to basically do some service password encryption. And I haven't done this one in a little while, so let's see what we got over here. Control C, config T, no, enable password 7. No, get rid of this. No service password. Service dash password. There we go. Okay, so now what you'll see if we look at the running configuration. Let's see. You should see it anymore. So you can't see it. Now let's try doing it a different way. Let's type enable secret Now, what's this going to show us in the running configuration this time? Now you can see we used an MD5 hash. And by using an MD5 hash, we've still got the same password in here. Now, the password is still Cisco. And if you don't believe me, look, I'm going to log out, exit. Now I'm going to type enable, and I'm still going to type Cisco. It's just that you're not going to see it.
Mike, you're not sharing your screen.
Huh.
There we go.
Well, that's
everything for the past minute or so.
now let's redo this. I really miss my Mac. Let me tell you, I'm going to get a new Mac so I can know exactly where everything is. I'll have a Windows computer to do work on and a Mac to use the rest of the time. So maybe I'll switch back to Red Hat or something. Config T. Let's get rid of this enable secret. Ugh. Control A. Takes you to the beginning of the line. No enable. Okay, so if we look at the running configuration here, we can see there's no service password encryption and no enable. Instead of doing the set a password, enable password Cisco, and then after I did the enable password Cisco, I typed service password encryption, I could actually use an MD5 hash on my password to make it unreasonable. And what is a MD5 hash? It's what's called a one-way hash. So here's the thing. If I put the word Cindy into a one-way hash, it's always going to produce the same output. But you can't go from that output and then figure out the name Cindy. So kind of keep that in the back of your mind. So if we just typed enable secret, like instead of password, and then over here we tell it, for example, the name of what we want to call it. So let's say it's called Cisco. Now when we look at the show running config, because I use the enable, let's see what it shows us. It shows us the enable secret. See, you've got it over here. You can see it's got this 5, which stands for MD5, and you can see that it's got a one-way hash. So that's kind of what we're trying to show you here. And really what we're dealing with is if we wanted, we could also create like a username and password local on the computer. So let's see what this would be for instead. So config T, let's do no enable secret, etc. So we can use another form of it. Now let's say we wanted to use a stronger encryption algorithm than say MD5. Maybe we want to use script, which is used by certain blockchains and cryptocurrencies. Maybe we want to use SHA-56, which is used by Bitcoin and other encryption technologies. So let's say we want to do this. So I'm not sure if this iOS will support it, but let's say we wanted to do a username.
Make sure to share your screen, Mike.
So let's say we decide to create a username and password, something more than a password. So let's do this. We'll do a username command, username. Now after this, we're going to name Cindy. Because Cindy likes routers. She loves to break networks. And then after this, we're going to tell it the algorithm type. Okay, so let's say we want to do a really good one. Algorithm type, do we have SHA-256? Yeah, we sure do. Okay, so now we've got a good, now let's type the secret, which is going to be the password. Secret. And then for the password, what are we going to type here? What are we going to type? Let's type it Cisco. Cindy and Cisco. Now we've got this. So now we do a show running config. Show run. It'd be helpful if I could type. What do we see here? What are we seeing over here? Oh, look at that username, and it's got a password. Oh, that's looking really ugly. Why is this thing so ugly looking? Why? Why is this thing so ugly? Because it's a 256-bit encryption algorithm. So we're going to get a lot longer, and it's going to be much harder to hack than MD5. That's why it looks longer. Well, not sure why this router is frozen, which is not a good thing. Let's see if we can get back into it. That's the thing. Sometimes these devices actually, so we can see that it's up and it's running, and we're good. Let's go back to our content. So what you've seen, what have we done so far? We created a username and a password with heavy-duty encryption. Then before that, what did we try to do? We created a username and a password with a local database. We created a password. We encrypted the password. So, this is kind of what we're really talking about. Now, let's look at what these security architectures would actually look like. I'm going to do that in the architecture section. So let's talk about some port security on the switch. When you're dealing with stuff on the ports, if I plug my cable into the port, I'm attached to the network. I want you to think about this. If I plug into the switch, I'm on the network. So I can hire 50 Navy SEALs. I can have three Marine Corps Scout snipers doing overwatch around the Navy SEALs. I can have firewalls, IDS, IPS systems. I can have dogs roaming the hallway. And if I've got a switch or a router like this, which is plugged into the network, and somebody plugs into one of these ports, every part of my security is gone. 100% of the security has been violated because somebody plugged in. So do we feel that this is robust? Security? The answer is no, not even one bit. So, we got to make sure that you can't just plug into the network. Exactly. So now let's look at this. What can I do to keep you from going into the network? Well, there's a lot of things I can do. How can I keep you from causing problems? Well, for one thing, if you go to plug in the network and I don't want you on my network, can I just say no, thank you? Remember yesterday, we had this identity and access management. We had Eva Doikia that left Bulgaria, who went to England, who's now living in Hungary, and she jumps on a plane, and she's going to stay with us to have a good time with my cat, Cindy. Eva Doikia and Cindy, they like each other. So Cindy plugs into the network with her computer, and it says, Cindy the cat, going to have a conversation with her friend Eva Doikia. Cindy the cat is welcome. Awesome, right? Now, Joey plugs into my house. Joey is a bad actor. Remember, Joey's the mean cat. I don't want that mean cat talking to Cindy's friend Eva Doikia. Joey tries to plug into the switch. An alarm goes off. Switch port shut down. Switch port shut down. Nobody's getting on the network. So that's called port security. Port security. And we can do it in a couple ways. We can basically make a switch and we can give it rules. If this MAC address comes in, open the port. If this MAC address comes in, close the port. Wow, think about that. Open it up, close it up. Wow, isn't this nice? So in other words, I can only allow the people on the network that want to be. Admission control. Think of it about this way. You got a highway. You want to get on the highway, you got to ask permission. You getting full that way? No, not at all. So when we're dealing with these things, we've got options. And each option gives us the ability to do things. So we can determine, how many users are going to be on a switch port. We can determine them. So basically, we do it as follows. We go to the switch port, and we get into the sub interface. I'll show you how to do it. And then we determine what kind of things we want to do. So we can set the maximum number of people or MAC addresses that come in inside of a port, for example. We can tell it to sticky learn, for an example. So I'll just show you some basic port security configuration, which we can do on any one of our switches over here. So let's take our switch over here. Let's get out of here. Let's turn on a switch. We've got a happy little switch over here. Hopefully, enable. We got a switch. So let's do a show IP interface brief so we can figure out the ports that are on this. Can you guys all see this? Okay, good. So let's say for gigabit Ethernet 1/3, we want to do some port security. So config let's do a show run. So we can also look at this. Show run int G1/3. Let's look at this. Okay, so this is what we've got on this. We can see the port is not shut down. Or at least we don't see shut down. Although we see it over here as status down, down, but it doesn't say administratively down. So let's go to this port. Let's configure it. So we'll go to config T. We'll go to interface G1/3. Now we're in the sub interface command. Let's tell it what kind of switch port we want it to be. We want it to be an access port. Mode access port is where you plug in the users. Let's say we're access. And now let's say we wanted to turn on port security. Easy. Switch port. Port security. It. We could tell it a certain MAC address or what to do in a violation, but that's it. That's how we turn on port security. That easy. So kind of hope that works. Wanted to walk you through that so you can see some of these things. Again, when it comes to things, the challenge is almost never configuration. It's always what are the things that you need to know to be great at your job. And I want you all great at your job. I want you all having miraculous careers and having just, the best time of it. So kind of keep that in the back of your mind while we're doing some of these things. Let's make sure we got all these things over here. So let's go back to, okay, so. Okay, just make sure you guys can all see me. So now let's go back to our content over here. Now that we talked about that, let's talk about some violations. Like I said, we can shut down, etc. So how will we look at it? So when a port gets shut down, how are we going to know? Well, we're going to look at it, the switch, and we're going to look at a show port security, and it's going to tell us what's happened. Everything with these things is about a show. So for example, if I want to show this, a show port security, we're just going to look at it. And it's going to be real easy for us. I'll show you what I mean. So we'll go back to here. We'll do a show port security. We can see which ports have it, and we can see what the action is. Shut it down. With a violation, shut it down. And here you can see if we wanted to get really, really careful, we can really lock these systems down. I'll show you a way if we really wanted to lock it down. So let's say in this particular case, go back, config T, to show you if we wanted to get really heavy duty, this is how much. So let's go back to the port so you can see it. So if we do a show run interface G, was it 1/3? Pretty sure it was 1/3. Okay, so if we go to the switch port, we can do more. We can really lock it down. If I wanted to, I could do a switch port. Think about int G1/3. And under here, what could I do? I could do a switch port. Then I could do port security. Then I could give it a MAC address. And I could tell it whatever I want it to be. Oh, wait, I think they like to do it this way, if I remember correctly. Now we did it. And then when we tell what do we want it to do, we can do, for example, a violation protect, switch port mode, switch port, port security, violation protect. So what I'm just showing you is what we can do is we can literally build a policy to make the switch port do whatever we need in terms of security. Now, when people say in the cloud it's extra secure, I'm like, are you kidding me? We can't do any of that. We lose all these things in the cloud. So the cloud internally becomes less secure because we've got our layer 3 stuff, which we'd like. But in the data center and the network, you can do our layer 2 and our layer 3 things. In the cloud, we lost all the layer 2. So anytime we get out of our data center, guess what? We're finding ourselves in a position. So now you can understand the concept of what we're doing. And then now if I were to look At these interfaces, we can see so much more. But, that's really what we're talking about. So let's talk about DHCP, or Dynamic Host Configuration Protocol. Actually, before we do, let's do this. Let's see if anybody has any questions. Let's take a couple minutes of questions. And then after a few minutes of questions, we'll come back and we'll start talking about some more content about DHCP and how do we implement it. And why is it such a challenge on a router to implement DHCP? And why is it a much bigger thing to do than it would be on a router when we implement DHCP? And there's lots of good reasons why. So let's make sure we understand those reasons. So let's bring in some questions. Chris, I'm trying to find StreamYard. Bear with me. I know it's here somewhere to see where the questions are coming from. But there's something with this Windows 11 with all of its virtual desktops and things. I can never seem to find anything. So let me try and find that. So I can, is it this one? Okay. Got it, Chris. Okay, let's bring in some questions that I can answer. Any recovery options for a lost password? Absolutely, Angelo. I think we'll probably talk about it. But what has to happen is you have to plug into the console part. And normally the register, I think the memory register is 2102, and you have to change it to 0x2148 or vice versa. And then what happens, you can recover the password. So yes, absolutely. But you have to be manually attached to the router to do it. Kaigoiso is it dedicating authentication to a Radius server or an Active Directory server best practices? Absolutely. That's what people do. Because when you've got 3,000 of these routers, you can't manually update 3,000 routers' passwords. And having 3, 4, or 5,000 routers and switches is nothing in a big network. If you have 3,000 locations, you have 3,000 routers. And if you've got a data center and things, you could have literally 20,000 routers. So yes, absolutely. It's a great idea, and it's always something you want to use whenever possible. Outsource the authentication to a TACX Plus server or Radius server or an Active Directory server. Good question. Well, we shut down the NAC with port security. DHCP is something totally unrelated, and that's basically how a host gets its IP address. So we use the port security command to actually set up things like 802.1x and port security. DHCP, we really aren't using the routers for DHCP. We could potentially make the router be a DHCP server, but nobody would really do that in production. No, there is some special things we have to do in DHCP, like with regards to helper addresses, which I'm going to explain why in a minute. But they're not related to LM. Chris, if you want to bring in the next one. Sarah Ahmed. Yesterday, we did layer 3 access list. Protect 192.168 from reaching 1.2.3.4. Port security is layer 2. The actual physical card. You plug in a hardware card and the MAC address isn't recognized by the switch, it won't allow it on. So layer 1 would be not giving you access to plug the wire in. Layer 2 would be not recognize your MAC address list. And then 3 is basically filter your packets. So think about it this way. If you can't get to plugging a cable in, you're really restricted from the systems. Then if you plug something into the network and you get shut down the second you plug into the network, if you're not allowed to be on the network, now you're secure. And then at layer 2, we can also make an access list as further security. And then we go up one lever to IP packets, and now we can do another set of filters. So really it's layer by layer. That's why the data center is always so much more secure than the cloud. Because we can do all this layer 2 and layer 3 stuff. And also, we're less of a high value target. Hack Azure, get access to all the customers. Hack Cindy the cat, you get to see Cindy the cat photos, which are really beautiful to see, but obviously less valuable than hacking into AWS or Azure and getting a third of the internet's customers. Looks like you got it there, Sarah. So let's go to the next one. Douglas, the packet has a header, and it'll either be a ICMP, TCP, UDP, and it'll be very obvious. Our teaching is great. Thank you so much. You and the guy doing CCNA on Stormwind are the best networking teachers. Thank you so much. I don't know who Stormwind is. I know I used to teach networking to Cisco people while working at Cisco, to people at WorldCom, which are now Verizon, to people at Comcast, which are still Comcast, and for people at, which was a company I loved working at, was called Riverstone, which became Alcatel-Lucent, which then got sold off to Nokia. So I'm thrilled to be here, and thank you so much for your kind words, Douglas. I love teaching networking, and cloud too, for that matter. Chris, if you want to bring in the next one. Great question. You can pretty much do it either way. Great question there. Pretty much either way is an option for you, based upon what kind of authentication mechanisms are there.
And that's it for right now.
Okay, well, this means we're doing good. So if everybody out there is here, if you could type hashtag CCNA and hashtag cloud architect all at the same time, it would make me smile. I know you're all there. Okay, so now let's have a little fun and talk about DHCP, or dynamic host configuration. Good, I see the CCNAs, the cloud hires and cloud architecture coming in. Makes me smile. I love it. So while that's coming in, which is going to be a bit delayed before I see it, let's talk about what is DHCP. Dynamic Host Configuration Protocol, also called DHCP, provides one of the most commonly used services on a TCP/IP network. The ability to get your host address automatically without manually configuring it. And by using DHCP, we don't have to run to every computer, manually put an IP address. Imagine running to 200,000 computers and giving them IP addresses. And then wait, you want to change the address. So you're going to go over to 200,000 computers and you're going to change all the addresses. Well, my world, that doesn't scale so well. So I'm looking for more scalability. What can I do to do a better job here? We're going to use DHCP. So DHCP, or Dynamic Host Configuration Protocol, is a means for hosts to pick up their IP address. That's it. It's a mean for hosts to pick up their IP address. So that's what it is. Without it, remember, we'd have to ask for it. So what happens? With DHCP, we've got these 4 messages. We've got a DHCP discover message, and I'm going to show you what that means. We have a DHCP offer, then we have a DHCP request, and then we have a DHCP acknowledgement. So let's act them out. Give me an IP address. That's called your DHCP discover. And literally what happens, the host comes up and it screams, give me an IP address. That's called the DHCP discover packet. Next thing what happens is DHCP server or servers say, I can give you an address. I can give you an address. And then the client says, I see 2 DHCP servers. I see one from Alexander. I see another one from Ruth. I'm going to request the one from Alexander. And then Alexander says, ne, echo, which means, yes, I have it. And here you go. So that's what goes on. So DHCP, as soon as the computer comes up, it sends a broadcast. DHCP discover. And the server's like, I heard your DHCP discover. I can give it to you. I can give it to you. And then the server says, I only want it from Alex. And then you got it from Alex and you say, I got it. I got it. And that's how this works. So the DHCP discover, big broadcast. And that, so there's going to be these 4 messages. And what are they really going to look like? You're going to look like this. You're going to see this DHCP discover message. And then the server is going to respond with that offer, and everything is going to be good. So that's how it works. So this all sounds great, right? Okay, but give me an IP address. It's called a broadcast. Now, what do routers do with broadcasts outside of their interface? They drop them. So I want you to truly understand the problem, and then you'll understand the solution. So let's walk through the DHCP problem. Here we are. Let's draw it out. We got over here, we've got Noni. think Abigail's on this call. Abigail's got this beautiful cat named Noni. She looks just like Cindy, but she's Noni. And Noni and Cindy, they decided to be really good friends. They want to talk to each other. They get on the network. They hit. Whoops, I didn't mean to do this. So let's go from here. Let's make our drawing a little better. Noni goes into the Noni switch. Switch plugs Noni into a router. We're going to walk through the whole routing. Now the router also has another subnet off of it. And this is where the DHCP server is. So the router is connected to this on one subnet. This is obviously on a different subnet over here. Noni's plugged into this little switch over here. Now we've got another router over here. And this router is over here. And this router is connected directly to Cindy's computer over an Ethernet segment. So Cindy's over here, she's here, but Noni comes onto the network. And Noni wants to reach Cindy. So Noni plugs in and says, hey, give me an IP address, DHCP discover. And what happens? That DHCP's discover packet is sent to the switch, propagated out all ports except for the one it came in on, reaches the router, and now it's on this subnet in the router. And the router says, this is a broadcast, don't forward broadcast out of my subnet, trash, and it throws the messages away. Now Noni's upset. Give me an IP address, I want to talk to Cindy. So she sends another request, and the router drops it because the routers don't forward broadcast. So Noni says, give me an IP address, I want to talk to Cindy, please. And her packet's lost. But Noni's a smart cat. Noni knows that there's a way to get on the network, but she doesn't know. So if any of you guys have seen the movie Born Free, Noni calls her friend Elsa the Lion that she saw in Born Free, and she says, Elsa the Lion, how are you getting an IP address? And Elsa the Lion says, Noni, routers don't forward your broadcast. And Noni says, meow, what do I do? And the lion screams and roars, and the lion says, you have to tell the router to forward your broadcast to the server. And Noni the cat says, how do I do that? And the lion says, here's what you need. You need something called the helper address, and you need to tell the router exactly where to send it to. So Noni gets on the computer. She telnets or SSHs into this router, and she told the router, forward all DHCP packets to the DHCP server. And that's something called a DHCP relay. So what this is called here is the DHCP relay, which says, take this broadcast request and forward it to this server. If this server is 1.1.1.1, we tell the DHCP relay to send it to 1.1.1.1. So we take the broadcast, and I don't know what the heck happened there. Okay, so we take this broadcast, and after we leave the broadcast, we say, hey, go over here. So now let's try it. Hold on, let's figure this out. Let's grab this thing. So now it gets to this device, it hits the switch, it sees the router. The router says, woohoo, I know what to do with your DHCP discover packet. Because I've got a DHCP helper address or a relay, send it to here. Now, the DHCP server now sees Noni's request and says, here, I've got something for you. Here's an offer. Now, she sends the offer back to Noni. But remember, Noni has to say that if they want it. Oops, didn't mean to do that. So now what Noni does is she sends a request and says, okay, I found you, you found me. Can I please take that address? Can I please accept that one? And Noni says this to the DHCP server. And then the DHCP server says yes. Now Noni's on the network. Now Noni's here. Now Noni wants to communicate with Cindy.com. So what does Noni do? She says, I know the IP address of Cindy because I went and got it via DNS lookup. Cindy is 2.2.2.2. So Noni goes to reach out She's got an IP address. And does she have a route to Cindy? No. So what does she do? She looks in the routing table. She's got a default route. What does she do? ARP, who has the MAC address for Cindy. Now the router is a proxy and it answers, I have the MAC address for Cindy. And the router says, I don't know how to get to Cindy, but I know if I go here, I'm one step closer. This router says, I know how to get to Cindy because it's connected. ARP, who has the MAC address of Cindy. Cindy says, I have the MAC address of Cindy. Cindy then sends her a packet here. It goes here. It goes to Noni. Now Cindy and Noni are taking selfies of each other's pointy little ears and their whiskers, and they're rolling around and they're having a good time. And they're collaborating on how they can take my network down, which Ethernet cables they can chew through, and all kinds of fun that they have. Now you know what they work. So that's called a DHCP relay service. And all that really does is you're telling the router to forward it to the next thing. So what's this going to look like? It's going to look like as follows. So let's assume we wanted to do this. I'll show you what it needs to look like in a minute. Let's say we're on a router. I haven't done one of these in a while, so bear with me.
Do you mean to be sharing your screen?
Yes, I do. Thank you, Chris. Let's say we'll go to this router. Let's just config T, interface G0/0, IP address. Let's just pick something we haven't used. I don't think we've used 172.1 IP, ADDR, 172.16.2.1, 255.255.255.0. It's an Ethernet link. We'll do a no shutdown on it. There's an IP. I think it's a helper dash address. So now if we do look at this port, and you can see the helper address. So what's really going on in this situation? So Noni's is plugged into gigabit Ethernet. When she does that, DHCP discover, give me an IP address method, it would hit this interface. And now the interface says it's a broadcast. Routers don't forward broadcast, but forward this broadcast to 1.2.3.4. So now you know how that works. And that is exactly what a helper address is and how we make DHCP actually work. Now we're going to briefly talk about some kind of device management systems. I am not a network management professional. Network management used to be its own CCIE because those of us that are system designers focus on routing and switching and architecture design. Some people focus on management. They're sysops people. I am not a sysops person. So I'm going to do the best I can with these sections. So, but I will, some of these things like Syslog, I know real well, and other things like SNMP and MIBs and things like that, that's not my world. So the key is these devices send a lot of messages. You saw them. Neighbor adjacency change, BGP change, port up, port down. By default, it goes to the console port. But guess what? You can also send them to a server. It's called the Syslog server. And then you can track all these messages. Now, why would we do this? We basically have 10,000 routers, and they're all spewing their logs to a server. Make a change on one router, you can see what it did to all 1,000 routers all in the same log. So we're logging so we can see the correlation between different events going on in our systems at different times. That's why we're using. And you've seen it. You've seen these messages. These syslog messages look like this. Interface change state to up, down. That's a syslog message. Excuse me. This is what happens when you're allergic to cats and you sleep with a cat every night. Or a cat decides to sleep on your head. So let's talk a little bit more about these kind of messages. When you get Syslog messages, they have layers of severity. Now, some of them are minor and some of them are there. So let's talk about, and thank you so much, Sharon and Angelo. Let's talk about the levels. So we've got 7 levels. Remember I did yesterday a debug IP OSPF hello? That's debug. It's a number 7 thing. It's not real serious. Why? Because I initiated it. We also have levels 6 and 7, 5 and 6 notifications that are normal. They're somewhat important, but not critical. Then we start getting level 4 levels, which are warnings, which are a problem. Then we get to layer 3 issues, which are or number 3 issues, which are errors, which become pretty important. Then we get to number 2 issues, which become critical events, really seriously. And then we get alerts, which are immediate action required. And then we've got emergencies, which nothing is working. And that's kind of your systems are unavailable. So in either case, none of these things are good. So how do you actually set up Syslog on one of these devices? Well, I guess we can show you. Let's show you how we set up Syslog. Again, it's relatively easy. So let's see where we've got this web browser. Okay, bear with me a second. So let's talk about how we would set it up. So let's go over to here. Let's share how we would set up Syslog. So let's go over here. So we've been logging to the console. Keep it this way. Let's keep the non-critical stuff going to the console. Let's say logging, monitor. We can see the debug stuff. And let's do a logging buffered with we'll keep a certain amount of things in the memory space for things that are moderately important. Now, what are we going to do? We're going to send big stuff to a host dedicated to a specific server. This is going to be our Syslog server. It's going to be a 1.2.3.4. We're going to send all critical stuff there. And then what we'll do is we'll send the logging. We'll tell it logging. So this next thing is called a trap, which we'll talk about. A trap is when something happens and you send an inform notification, and we'll send warning levels anytime they occur. So now what you can see is that's really all it takes to change the logging. So we see a show log. I'm not a sysops person, so this is not my world. But you can see in the logging, we've got what we're logging, what we're debugging, et cetera, et cetera. Now that we've talked a little bit about Syslog messages, let's talk about network time protocol. So I want you to think about this. Let's assume you have 20,000 routers in your network. Let's assume something happens on Monday, and you've got another. And let's assume you got a cable cut, and this cable cut affects the routing tables on 10,000 routers. Now, if this cable cut took the network down, you'd want to know about it, right? You'd also want to be able to correlate it to see what happened. So imagine if you had a log, and let's take the precision out of the logs. Let's say it's midnight, 12 p.m. midnight, and one device sends you some information at 11:30 and says it's broken. Another device sends it to you at 11:45. Another one at 10 o'clock. Another one at midnight. Another one at 12:30. And it's all the same problem, but spread over 2 hours. Can you find it? No. Now, if all your devices were synchronized to the nanosecond, and if every device that you had a problem at 11:56 with 30.0700.7 seconds, and you can correlate that this one thing happened and within 5 seconds the whole network went to heck, you can figure out what went wrong. So we have to have synchronized times on our computers. That's why your computer usually syncs itself to Apple's time or Windows, Microsoft time. And what that is, it's something called Network Time Protocol. It's an IP protocol designed to give times to IP-enabled devices. And that way, all your timestamps and all your logs are going to be the same. So, realistically speaking, we connect to an NTP server. Your computer is connecting to one, I promise you. Your iPhone is. When you get on your iPhone, it's got a clock. You know, how does my iPhone right now know that it's exactly 12:52? It's pulling it from somewhere. That's what's going on, is it's pulling it. And because it's pulling it, I can see it. And because I can see it, I know what it is. So these are kind of those things that are super important. Now, could you just set a clock? Sure, you absolutely could. You want me to show you how to do it? What we're going to do is we're going to set the clock. And we're not going to put the time. We're going to give it the time zone, etc. And it's pretty easy. How do we do that? Well, I'm going to show you in a minute. Here's what we're going to do. We're going to go to our router. We'll tell it the clock time zone. Now, let's say I'm EST. Now, what is the world centralized time zone? You know, we Americans like to believe it's New York, but it's not. It's Greenwich Mean Time, which for the most part is UK time, except in the summertime. So we're going to work off of UK time pretty much and everything. And what is it going to be? We're going to be looking for hours from UTC or GMT. So we're off by 5. We're -5. That's why when it's 9 o'clock for us, it's 2 p.m. in people in England. Now, do we want it to include daylight savings time? Yeah, we do. So clock, summertime, EDT. I think it's reoccurring. Now our device is going to be set. It's going to know where it is, when it is, and when it is, and all things are going to be good. So I hope that was pretty clear to you why we did it. We want our devices to be there to give us times. And now let's say we wanted to pull from the time server. That's okay. All we're going to do is we're going to tell it where to go to, which server or servers to go to. And of course, we could use more than one server. Why? In case one server doesn't work. So NTP server, we're going to give it an IP address, right? That's 1.2.3.4. Add another one. These are obviously made up. Done. That's how you configure NTP. So as you can see, you know, it's never, the challenge is never configuring these things. It's just knowing what you need and when you need it. So let's walk through some more things. Okay, let's now talk about another protocol called Cisco Discovery Protocol. Now, it used to be when I went into networking, all these routers ran something called Cisco Discovery Protocol. And it was a layer 2 protocol, and routers identified itself. And it is the coolest protocol in the world, unless you're concerned about security. And then it becomes a very uncool protocol. So let's show you what CDP is, or Cisco Discovery Protocol, because it's a very, very useful diagnostic tool. So let's get off of this router. Let's get off of this device. Let's get off of this device. Let's go to this device over here. And we're going to enable CDP so you can see it. So right now I'm going to do a show CDP neighbors. And you should be able to see, oh wait, I already turned on Cisco Discovery Protocol. I usually turn it on, but it's by default to shut off. So look what happens. I now know I am sitting here on router 1 over here, and I know that I am connected to this device on this port, to this device via this port, and to this device via this port. So that protocol is actually showing me who I'm connected to. Now, if I want to see really good, look at this. Show CDP neighbor, and I think there's a detail command I can do after this. That I can now see my neighbor. This is I mean, this is why we shut it down now. I can see the neighbor that I have. I can literally see what kind of software they're even using on the router. I now know the weaknesses and vulnerabilities in the router by looking at it. I can see their IP addresses. I can see on what's port. I get all kinds of information about my neighbors. This gives me all kinds of ability to map out my network, to troubleshoot it, which it does. But it also gives me a whole lot of information if I wanted to be a hacker too. So, with any of these discovery protocols, look at them. Now, by default, CDP is disabled. I turn it on because when I configure my networks, I like it on. And when I'm done configuring them, I shut them off. And if I need it, I can turn it on for troubleshooting. But realize once you do that, the hackers can see if they're on your devices. They get a lot of background to what's going on. And that's not my favorite thing. So because of that, that's not really the ultimate goal that I try and do things that way. I try, much harder to make sure what we're doing and think, et cetera, et cetera, et cetera. Now, next, let's see what else we want to talk about over here. Now, the CDP was a Cisco protocol, but of course, the IEEE, or the Institute for Electrical Engineers, came up with a version that would be useful for all network devices called Link Layer Discovery Protocol. And what is that? A layer 2 protocol for network devices to find other network devices. So guess what? Same kind of concept, but you can use it with Cisco and Juniper stuff. So we're going to get into that next, which is a pretty important topic. But before we do, let's see if any of you guys have any kind of questions that we can answer for you. So if any of you guys have any questions, great. By the way, if you're having a good time, if you can hit the like button, subscribe to the channel, tell a friend, et cetera, et cetera, et cetera. That enables us to grow. Let me see. So those kind of things are always appreciated by us. Likes, comments, subscribes, et cetera. So does anybody have any questions? Before
we don't have any questions just yet. So let's see if we get some that come in the next few seconds.
Okay, if any of you guys have any quick questions, I'd love to answer them. And if not, guess what? We'll keep going to content. We'll have some fun. Today's content's not super complicated. So
this is not a question, but I'm going to put this up here because it happens every day to us. Somebody, it's not a job offer, but you know where this is going to.
Hi, Mike. I just got an email from a company that emailed you 2 weeks ago asking question 1, how much notice to provide? Eugene, typically speaking, you should give at least 2 weeks notice. Question 2 is career aspirations. Love to help you with that. And salary requests, etc. I'm happy to answer your questions if I actually know the depth of what you desire to do. But first and foremost, Eugene, congratulations. I got to tell you, every single time I get one of these messages, I am blown away and extremely excited. And I know I get one of these every day. But the key is, Eugene, I'd love to guide you and help you. So how much notice? Typically speaking is 2 weeks. Congratulations again, Eugene. I'm just so happy for you. And I get at least 1 or 2 people every single day that says this, but I'm just so happy for you. So what I would say is definitely 2 weeks. If they've asking your salary request, what is your current salary? What is your past salary? What is the average salary? What is the average salary that company pays? Do some reconnaissance and figure it out. 3 is, I don't know what kind of job it is. If I knew the kind of job, although I think I know what kind of job it is, because Eugene, your name is pretty darn familiar to me, I could easily guide you in the right direction. So I don't exactly know which job. I don't exactly know which employer to help you with that. But typically speaking, at least 2 weeks notice of your previous employer is very good. Most importantly, though, congratulations, Eugene. I don't know if it's a network job or a cloud job, whatever it is. I'm so happy for you. I'm just so happy for you. I'm beyond thrilled. So Eugene, congratulations. Super, super, super excited for you. And just thrilled. Congratulations. Go and enjoy your new life. But if you've got some questions and you want to ask a more specific question, we'd love to be able to help you. Jim, are we going to make a buck like the cloud buck? I don't know. Our world, realistically speaking, is cloud architects. Do I have a desire to do something in the networking space? The answer is sure. Go back and do networking. It's really where my heart lies. I'm kind of busy, and I don't know if I have any time to write a book. I think our team is definitely focused on writing one book on another cloud in the next year. At least it's a goal of mine. I do plan on creating a leadership book based upon my 25 years of leadership. And regarding that, next after that, maybe networking thing, but it's not on my extreme to-do list by any stretch of the imagination right now. We're kind of bogged down. Right now, I'm more concerned with taking care of veterans and making sure every one of my students gets a great job. Because for us, it's all about, it's a family. Go Cloud Careers is a family. My students, they talk to each other across continents, and they're really great. So it's definitely something I'm considering. But right now, my biggest focus is on getting all of our students graduated and hired. Jazz, it is so good to see you. I'm thrilled to see you here. Also thrilled to see you with your Blue Wrench. And of course, great day for networking. Absolutely. Eugene, DevOps engineer and cloud operations. So Eugene, that's where it's going to get tricky. When you go to the operations side, the salaries are typically a lot less, but DevOps is still really there. So realistically speaking, a good DevOps engineer should be in the range of, $90,000 to $180,000 a year based upon how good you actually are. Eugene, what will determine what you're going to be paid is both your technical skill, but beyond that, really it's about your emotional intelligence, communication skills, presentation skills, leadership skills. That can double or your salary or more just by being good at it. So what I would say is 2 weeks notice. I don't know your level of background or experience, so look at your level of background and experience. Look at what you do compared to the other person, and then and then you should be able to do something. But first and foremost, congratulations. DevOps is a fantastic career. It's not one of my more careers that I specialize in more because I tend to specialize more on the architectural side or the leadership side, but I'm so happy for you. So go search what the DevOps engineers are being paid by other similar sized companies. So for example, let's pretend it's AWS. What is Azure paying? What is Google paying? What is Cisco paying? What is Dell paying? That's going to be where you're going to get your information. Then from there, what you have to do is you have to figure out, are you better or worse than average? And if so, where? Are you more emotionally intelligent with better soft skills? Ding, 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 ding. Wow, you're going to really do good. Or are you more technical? Okay, show how you can win technically. The real key is for you to find that special strength. For me, it's my leadership, my communication skills, my executive presence. That's what makes me stand out. That's what I do. It's also my business acumen, but whatever that is, find out what it is, and then find out how to position that to show that you're better than the rest, and you'll get paid much more. So with regards to negotiating your higher salary, the Harvard negotiation project came up with the concept of a BATNA, which I agree with. Basically speaking, you have to figure out what is your best alternative to a negotiated agreement in terms of salary-wise. What is that? If you have 3 offers, you can figure out if this one doesn't come in, go somewhere else. If you've got 1 offer, can you afford to lose that job? If so, what do you need to do? Those are the kind of things that would be there. That's the kind of training we have. So Chris Voss has some good negotiation work. The Harvard Negotiation Project does. Getting to Yes has some good information. The book, Getting Past No, also has good information. So there you go. Okay, this is a good question, Asaya. So you get on your computer, you got an IP address. For some reason, it's not working. You maybe your computer just happens to be on the wrong subnet. If you accidentally tell your computer to give up its IP address and ask for a new one, sometimes you get lucky. That's what the DHCP release says, and the refreshes say DHCP releases say give up the address. DHCP requests say give me a new one. Great question there, Asaya.
And we had someone ask about the leadership program.
That leadership program is open and available and ready for purchase on our website.
And the live class part will begin Friday, February 18th.
Yes. So the main version that's all self-paced is available today. The live version begins on February 18th.
That is currently the last question.
Okay. Well, we got through these questions. Let's do some more network training. So while we're doing all these network trainings, let's talk about NAT. So here's the problem. 2 to the 32nd minus 2 addresses seems like a lot. It's a few billion. But you think this is a free? Okay, I'm not even sure what that question is. So we ran out of IP addresses a long, long time ago. So what happened was the Internet Engineering Task Force said, hey, wait, because we don't have enough public addresses, we've got to find some way to basically come up with something that's going to work. So what they did is they created a request for comments. What is a request for comment? Quite frankly, a request for comments is a specification from the Internet Engineering Task Force. So they came up with the concept of RFC 1918, which was the specification 1918, which was called address allocation for private intranets. So private addresses that you use inside of your organization. And by using internal addresses internally, you're good to go. And by using external addresses externally, use public addresses. So what is this private address space? It is 10.0.0.0/8. The next set of private address spaces that we have is we have the 172.16.0.0/12. What does that mean? It means 172.16.0.0 all the way through 172.31.0.0. The last set of IP addresses that we have are the 192.168/16. What does that mean? It means it covers 192.168.0.0 all the way through 192.168.255.255. So we've got a lot of private addresses that we can use. Now that's perfect private addresses. Now, let's assume this for a little bit. Let's assume that we were going to buy another company. What are the chances that company 2 is using the same private IP addresses that we are? Very high. Why? Because the Internet Engineering Task Force told everybody inside of your organizations, use the 10.8 address space, the 172.16/12, or the 192.168/16 address space. So every organization in the entire world is using the same addresses. So what are the chances that you're overlapping with someone else? Really great. Really great. So Cindy the cat has an address. Cindy the cat wants to talk to Jazz over there in New Jersey. Cindy the cat now needs to leave her Port St. Lucie home and be seen on the public internet to go over to reach Jazz in New Jersey. So Cindy has to take her private IP address, which might be 10.1.2.3, and turn it into something public like 75.1.2.3. By doing that, Cindy has a public address. So Cindy wants to go to the internet, she needs a public address. Oh, wait. What if Cindy works for Go Cloud Careers and Noni works for Go Cloud Architects? Same company, by the way, but that's neither here. So they're working for two separate companies, and Go Cloud Architects uses the 10/8 address space, and Go Cloud Careers uses the 10/8 address space. Now, how are those two cats going to talk to each other? They can't. So they've got two options. Either the one side says, I'll no longer be 10/8, I'll be 172.16. They change their address, and Noni and Cindy are talking to each other, having a great time. Now, Noni decides to translate her address to 192.168, and Cindy translates her address to 172.16. Now they've got beautifully unique addresses. So network address translation is used to translate one address to another. It's commonly used to connect to the internet, and it's very commonly used to connect external organizations that have overlapping IP addresses. In fact, that's usually the most common use of it. Where did NAT come from? Well, it's an IP specification, so that means there's a request for comment. So, you ever want to learn about something? Don't go to the Udemy video. Go to the source. What is the source? The request for comment. Ask any CCIE. that's got a CCNA number of less than 10,000 back when the exam was really hard, and it was a 2-day exam, we read these RFCs. We read the actual specification. That's how we know these protocols so well. Want to be great? Read the specification. You know how much the specification costs? Free. It's free. Go to the Internet Engineering Test Press. Look up your RFCs. You'll find it. The RFC for NAT is 3022. 3022. So now with NAT, we're going to have a couple concepts in NAT. We're going to have static NAT. What is static NAT? Send you the cat. Always equals 1.2.3.4. That's static NAT. One-to-one mapping. Always the same. So let's think you had a web server in a private subnet. You give it static NAT. Why? Because the public address is always going to be the same thing that goes to that server. It's static. What do we know about servers? They have static addresses. What do we know about static network devices? They have static addresses, manual, because we can't have our stuff moving around. So for stuff that you need, like a server, they use static NAT. And relatively speaking, it's a one-to-one mapping. Map this address to this address. Constantly, one-to-one mapping. One address to another address. Now, dynamic NAT's going to be a little different. Dynamic NAT's going to change. Dynamic NAT will what? One address, two address. It could be for 5 minutes, or it could be for an hour. It could be for a long time or a short time. So kind of keep that in mind. So static NAT, constant, consistent. Dynamic NAT, not static or consistent. So let's talk about the third kind of NAT. This is called PAT, NAT overload or port address translation. What is NAT overload? If I got 1,000 servers and they want to be public on the internet, I need 1,000 public IP addresses. If I've got 50,000 employees and my company that want to connect to the internet, they really need 50,000 IP addresses. So, not a good thing, huh? So if I use static NAT, one-to-one NAT, and I've got 50,000 computers, I need 50,000 addresses. Oh, wait, we ran out of addresses a long time ago. So what is NAT overload? NAT is one-to-many NAT, and that's what most organizations use. So when you get 1 or 2 or 3 public IP addresses and you stick them on the firewall and you translate 50 addresses into a single public IP address, that's NAT overload. So what happens is it uses an address and a port number. And that's why it's called port address translation. So by doing the things, it's going to be in a situation. So this is a great article, a great slide that you can find in that book. I liked it so much I wanted to borrow it, but this comes straight out of Cisco. So get this from your Cisco documentation. You see how you've got these 3 devices? 10.1.1.1, 10.1.1.2, 10.1.1.3. They're all able to reach this thing because you've got the address, but they're using a different port. They're using different port numbers. And by using different port numbers in each case, we're able to segregate them and separate them. So they look unique from each other. So that's what we're talking about with regards to NAT overflows. So how do you configure NAT? Well, let's show you. Very simple. With NAT, we've got something inside and something outside. Inside and outside. So what do we mean by inside versus outside? Well, let's do it. Let's configure static and dynamic NAT. Let's have some fun with it. Let's show you how kind of systems work, etc., etc., etc. And we'll show you, and it'll be fantastic. So let's go back to this device. We'll go back to our EVE-NG server. We'll pop it up. We'll configure some static and dynamic NAT. Let's close this lab. Let's create a new lab. Add a new lab. Let's call it NAT. Okay, we'll open up our NAT lab. Let's add a node. Wrong one. Let's add an object. Let's add a node. Let's add a nice little router over here. Happy, nice router. Let's turn the router on. We'll do some NAT on it. It'll be all kinds of cool. Let our devices boot. They take a few minutes. While we're waiting for this to come up, I'm going to give you some advice that I've learned the hard way. If you have a 64-core workstation with a couple of GPUs in it, and you've got an EVE-NG server running on a 24-core system with about a half a terabyte of RAM, and you've got 6K video cameras and studio lighting, by the end of the day, it gets pretty hot in your office, no matter how much air conditioning you could possibly use.
You like that hot yoga though, Mike.
I do like hot yoga, so I do have a special room in my house that I heat to 130 degrees to practice yoga every day because it's good for my neuropathy pain and my reflex sympathetic dystrophy pain. But I will say this, my office that's 96 degrees all day long does at some point get a little hot. Of course, my arthritis feels better in the heat, so I guess there's both sides of it. But computers generate a lot of heat for those of you folks that have not worked in data centers. All right, come on, you slow router. She'll be up in a minute. Okay, here we go. Happy router now. So we're just gonna have a little fun with this. I'll show what we mean. We need some reggae music when we configure these things. Let's give it a host name. Let's make it clear to us. We'll call it a host name. We'll call it NAT router. We've got our NAT router. Let's do this. Let's go to interface. Int G0/0. Under here, let's put an IP address on it. Let's say 10 IP ADR. Let's say 10.1.1.255.255.255.255.252.2.0. Let's say over in here, let's do another one, int. Let's do a no shutdown. Now what we're going to do is we're going to go to another one, int G0/1. IP address, let's put another subnet, 192.168.1.1, 255.255.255.0. That's what we need. We need some reggae music in here. I haven't heard any since this morning when I was practicing yoga.
We need some reggae version of Jeopardy music. That's what.
Yeah, that would be good.
I'm sure I can find that.
See if you can find some reggae Jeopardy music for the next project. That would be really great. So let's get out of here. Now let's set up our NAT. We'll do an IP NAT inside. Now what we have to do over here, we have to tell it the source. So we're going to determine what we want to be the inside. Now remember, the inside was the first thing we did, the 10.1.1.1. So let's tell it what the source address is going to be. Let's say 10.1.1.2 will be one, and we're gonna map 10. So we're gonna map. Let's say we've got a 10.1.1.1. Make sure I got this right. We've got the 10.1.1. Let's say we're going to translate .2, and let's say we're going to translate .2 into something on the exterior 192.168.1.2. Now let's say we're going to also take a .3. .3, and let's turn that into another one, a .3. So what we've done here is we've set this device to translate 10.1.1.2 to 192.168.1.2, and then I just messed up. Okay, so let's look at our running config and make sure I don't have too many funny NAT things in here. What we should see is, okay, we've got a mapping of 10.1.1.2 to 192.168.1.2. And then over here, what you can see is we've got a mapping of 10.1.1.3 down this. Now, the only thing we haven't done yet is we actually have to tell the interfaces who's inside and who's outside. So if you'll recall, we had the interface gigabit 0/0, which has that 10 address space. And over here, we're going to tell it to be the inside of the NAT. That's the inside interface. Now, we did this. We actually crashed the router. We got a memory error, which, this should not happen, but everybody's got bugs. So, kind of keep this in your mouth. So, but we also have to make sure we do the interface. Let's go. Remember, we also did the external interface. So show IP int brief. Make sure we get the external interface. Okay, the external interface is going to be a config T. Now, when we go over here, what we're going to have to do is interface G0/1, and then we'll do IP NAT. Outside. Now that's going to work. We'll do a no shutdown on this. So if I do a show IP interface brief, can anybody tell me in the chat box why these interfaces are going to be down? Can anybody tell me why these interfaces are down? Now, these two are administratively down, which means manually shut down. But can anybody tell me, this is the NAT interface, but can anybody tell me why these things are down? In the chat box, tell me why it's down. Anybody tell me in the chat box? Somebody tell me why these two interfaces are down? Ferdy, exactly. There's no cable plugged in and there's no connected switches, albino. It's not connected. So if we want one of these ports to go through, then we're going to have to plug it into something. So let's say we're going to plug in a switch, just to give you an example. I'm going to make sure everybody sees this. I want to make sure this is clear. We don't have layer 2 and layer 1 because we've got no connection. So I'm not sure how long it's going to take for the switch to fully come back, but let's just plug in a switch. Now, at some point when that switch comes up, we're going to, here we go, interface gigabit Ethernet change state to up. So now we can see that the one interface that we plugged into a switch is up. So now you know why. It's manually there. It needed to be set. So for the people that got that right, very, very good job. Very, very good job. You're starting to get it. You're starting to feel it. If there's no cable plugged in, there's nothing going to work. Why? Because there is no network. So woohoo, you guys got it. I'm very, very, very excited every time I see these things. Because you guys are getting it, no cable. You understand the layer 1, the layer 2. You guys are doing great. So now let's get back to our content that we're talking about over here. Now we've talked about some NAT. Let's talk about quality of service. So what is quality of service? You know when you go to the airport and you want to get on a plane and they're busy, and then you bought a first class ticket and you don't have to go in the big line, or you pay for the frequent traveler number and you don't have to wait so long? It's quality of service. When you go to the store and you're a VIP and they give you access to things, that's quality of service. So quality of service enables you to treat different traffic differently. And there is a lot of reasons why you would do it. For example, let's say you've got a network. Remember when I made that access control list with OSPF and intentionally broke it? And all of a sudden we lost the routing, we lost the control plane. So how important was that OSPF traffic to our network working? Critical. It's the control plane. Now let's say we've got a network, and in our network we've got people that are downloading music from Collie Buddz, Damian Marley, Ziggy Marley, Bob Marley, UB40, and Bobby McFerrin, which is not reggae, but the song Don't Worry, Be Happy is pretty popular in Jamaica, as well as reggae music. So now we've got all this stuff. What if Cindy the cat was listening to reggae all day long, and Cindy the cat decided to download the entire reggae library from the internet? My cat loves reggae. So well, I practice the yoga with listening to reggae, and she's in there with me in yoga, so I assume Cindy the cat loves reggae. Anyway, so the cat and I are listening to our reggae because it's important to us. But Cindy the cat wants to send a message to Noni the cat that there's a wolf around and they need to hide. So when Cindy the cat needs to send that message to Noni the cat about the big scary wolf and dog that are together as friends, if that message doesn't get to Noni from Cindy, Noni could be fighting a wolf, which is not a good situation. So that message from Noni to Cindy or Cindy to Noni that says, stay in your house, cuddle up with your owners, don't go out, there's a wolf. That's a pretty important thing. So I want you to think about this. Think about what traffic matters. So when traffic, if we've got all of our phones on voice, hey, yeah, and we can't place a phone call, we are in trouble. So we have quality of service to let us prioritize the kind of traffic that we need. Prioritize voice, prioritize video, prioritize signaling. Why? Why does this matter? Well, let's talk about some constraints that we have. We can have a constraint with bandwidth. What is bandwidth? I've got a 10 gig link. I'm sending 10 gigs of data. Guess what? The link is full. That's a problem. Now, if I can prioritize voice, if there's congestion, voice always gets through. OSPF always gets through. Cindy the cat's data always gets through. Mike's data always gets through. Everybody else's traffic gets through only if it matters, if there's capacity. That's QoS. So think about this. Think about the security impact of the QoS. I've been advising people to use QoS for 20 plus years, mostly for network security. Why? I advised a bank, it was a global bank. I said, you must put QoS on your networks. And they said, Mike, you're an idiot. We have gigabit Ethernet to the desktop. We're never going to fill up our gigabit Ethernet ports. This was 15 years ago. I said, you have voice over IP, and when you get one worm, that worm's going to replicate, and it's going to go gigabit Ethernet to every desktop, and it's going to shut down your entire phone network. The customer said, Mike, science fiction. Nobody can fill up a network that's got 14,000 gigabit Ethernet ports. I said, I promise you, one worm and you're done. 3 weeks later, customer gets hit with a worm, filled up 1 gig to every one of their 15,000 financial advisors that were using that system. All down. They come back to me and said, Mike, you got a security problem. I said, no. We told you if you don't use QoS and you get infected with a worm, your network will be down. They said, yeah, but I said, you didn't use QoS. You got infected with a worm and your network is down. I'm here to help you. Now let's set up the QoS policies we talked about in the past. And then they did it. So QoS, I like to think of as security. But let's talk about the constraints we have for data. So bandwidth is the amount of stuff you can send. Delay is the latency. So Eva Doik is over there in Hungary. I'm over here in Florida. We decided to buy a wire between her house and my house. And that way, she can do video watching and taking care of my cat Cindy. We can talk. She can help me with a blockchain project that I'm working on. I can talk to her. Everything's good. We've got a wire between us. It takes 6 milliseconds for me to reach Eva Doik over the wire. 1 millisecond for me to reach Chris. 6 milliseconds. That's delay. Now, if it's always 6 milliseconds to reach Eva Doik, it's probably okay. But what if packet 1 is 6 milliseconds? Packet 2 is 3 milliseconds. Packet 4 is 50 milliseconds. That's called jitter, which is variations in latency. That's a problem, and voice and video applications don't do it. Why? Imagine sending a conversation and one word arrives before the previous word. It's not good. So bandwidth is the amount of stuff we can shove in a pipe. Delay is how long it takes to get there. Jitter is variations in latency. And the last is packet loss. What is packet loss? You lose data. We do a ping and we lose some packets, packet loss. So just kind of keep that in your mind. So we're using QoS or quality of service to make sure that our important stuff gets through. By making sure our important stuff gets through, we don't lose it. So we don't have packet loss of critical things. We minimize the jitter of our critical things because we always allow the most important stuff first. So you got a platinum card. Get on the airplane first. QoS. You try to get on the airplane. They form a queue. First class goes first. People that go next goes second. That is the same thing. It's killing quality of service. Try to see what we got over here. So what do you think is latency sensitive? Real-time traffic. What is real-time traffic? Voice and video. That stuff, highly sensitive to variations in latency. So let's talk about the kind of things that we're talking about. With voice, realistically speaking, we got to deal with about 150 milliseconds or less. Any more than that, we're going to have problems. Jitter, 30 milliseconds or less, and that's pretty bad. And packet loss of 1% or less, that's at minimum. So some video can go from as little as 384K all the way to about 20 megabits per second. Jitter again, the thing, but video again, you can't deal with more than 1% packet loss. Like 0.1 and 1% is pretty much about the same thing. Now, there's one other thing that we can actually do. On the routers, we can actually come up with a classification. We can mark our traffic. So we can have a packet come into the traffic. We can look at it and say, woohoo, pretty important. Set this packet as high priority. Now, that's really not something we're going to talk about on the Cisco Certified Network Associate a lot, but that's something called an NBAR, network-based access control recognition. And basically, you can use that to match a packet, and you can basically configure the packet to be of higher value, et cetera, et cetera. So let's talk a little bit about queuing. Now, if you're not American, queuing is easy for you. If you're American, you have to think about it. So for the Americans there, the rest of the world calls a line a queue. So when you're in an airport in England and they say form a queue, basically means a line. Now with queuing, we're going to have a lot of ways that we can schedule our data. For example, we can, let's just draw out what a queue is to make it kind of, I'm going to draw out what a queue is. I want to show you what it is to make it clear to you. So let's say over here, let's say we've got our router. And this router has this connection to another router. Get rid of the fill out of this. Let's do this. Great. Let's pretend this is a 1 gig link between yourself and AWS or Azure. Let's assume some of our traffic is really critical voice. And we decided to prioritize that. And we give 50% of the capacity to the link, to the voice and video. And then we say, Cindy the cat's traffic is really important. So Cindy the cat gets 25%. And then everything else that's not voice or video or Cindy the cat can get up to 25%. Now, if there's no traffic from Cindy and there's no video, the other traffic can use it. But if there's contention for traffic, Voice and video goes first, Cindy goes second, and somebody else's goes third. That's queuing. Now, the kind of queuing I'm describing here is something called priority queuing, meaning prioritize 1 versus 2 versus 3. But, that's realistically speaking what we're talking about. It's just one form of queuing. So queuing is about making sure your devices can get there. So, maybe we should draw on one more thing and talk about queue scheduling. So while we're at it, let's add a queue schedule. So you can think of this because you're going to see queues and applications. Basically, you look at this as a router. We can look at this as a server because we'll see queues outside of networking, which goes to a queue like an IBM message queue or an Amazon SQS queue, whatever. I think you can use Apache Kafka for a queue. And then we've got another server. If we've got a server that wants to send messages to another server, we can stick a queue. And what can happen is the server can send all of its messages into the queue. And all these messages are going in the queue. And then ultimately what happens is the queue can be drained one at a time when the server is ready for it. This one message comes out, gets drained, goes through, out. So we can use queuing for lots of reasons to make sure we don't lose traffic. Queuing is used in the cloud. It's used with servers. It's used with databases. It's used with routers. So we're talking about something that's pretty common stuff. I just wanted everybody to understand what is queuing and why. So how do we schedule this queue? Well, I just showed you priority queuing, but we could do it a lot of ways. We could do a round robin. We could basically have 4 queues and just 25% to each one. We can basically set up percentages like I just showed you in a class-based queue. We could do priority where only you go and then you go and then you go. But we can do several different kinds of queuing things. Now, since we talked about queuing, let's talk about policing. Policing is a little different. Policing is about admission control and access. So let's look at this. Let's look at this and let's look at access. So let's draw this out so I can show you. Let's go over here. So now let's pretend you've got your, let's call this a router. Got a router 1. Router 1. Router 1 has a 10 gig connection. So let's come up with something that looks pretty thick. We've got this 10 gig connection between these devices. Now over here, I've got a big server. In fact, the server has 64 cores, got a terabyte of RAM. You know what my server has? My server has a 100 gig network card. And here's the worst part of this. This server is plugged in to this switch with a 100 gig connection. Now this one server, let's say the server is sending 30 gigs of traffic to router 1. Now router 1, when it gets 30 gigs of traffic, can it send 30 gigs to router 2? From router 1 to router 2? Can router 1 send 30 gigs per second of data over the link from router 1 to router 2 when it's only 10 gigs? No. So what I can do is I can create a policy that I can say drop. And what policing is drop greater than 1 Gbps or 10. I can create a policy, and this is called policing, that will only allow a certain amount of traffic onto the system. That's called policing. So have you ever seen when you're on a highway and the highway's congested and the police go to the exits and they don't let you on, that's admission control. What's that called? It's called policing. It's the same thing. Identical thing. That's called policing. Shaping your traffic. So if you don't let it in the router, it can't fill it out. So policing basically tells the routers to basically just see this, just drop it. Okay, so before we get into first hop router redundancy protocols, which is a topic I absolutely love, I feel like we should bring in some questions, because I feel like we're going to go into something that gets pretty complicated pretty quickly. And with that, we should make sure we get some questions. So Chris, are there any more questions for me? Ferdy, I'm not completely sure what you're saying there, but yes, I'm assuming you're referring to QoS, and that's exactly. We do voice first and then data. Exactly, that would be the thing. That's why we're using these QoSs.
And no other particular questions right now, so we'll see if any come in.
If you guys have any questions, let me know. I haven't seen any, but it's hard for me to believe we're covering this much networking stuff and there's no questions. But if there's no questions, we're always happy to keep going. Reggae router, yes, absolutely. We need that. Earl, I would love a reggae router. That's one of something I totally love. Everything is going to be all right. Angelo, yes, QoS. Well, Angelo, the point is you're going to need both. Remember, a VLAN for voice is layer 2. And yes, we've got layer 2 things, but ultimately we're going to be on a layer 3 network. So we're going to need both QoS and VLANs for voice, Angelo, both. It's not an either or. Good question, though. And then, Chris, you can bring in the next one if there's not another one.
Not anything right now.
Okay.
Oh, here we go. Now they're starting to come in.
Yeah, Albino has a question. Bandwidth is basically the same as max throughput. QoS does not control the bandwidth. QoS determines what traffic can be sent ahead of what other traffic. If you've got a link that's got 10 gigs of bandwidth, it's always going to have 10 gigs of bandwidth. Where QoS comes into play is when you've got 100 gigs trying to shove itself out the 10 gig pipe, and you determine which 10 gigs goes versus which stuff you drop. That is a good question there, Brian. Very good question. Can I explain about dropping? I don't know what you mean about dropping, Albino. I mean, because dropping could be anything. The only thing that I think you can assume is regarding dropping frames. Like if you've got 100 gigs trying to come in and you blocked it at 10 gigs, the rest of the 90 is dropped. So kind of look at it this way. Let's assume you had a cup that can hold 300 milliliters. Once you pour 300 milliliters in the cup overflows and it all gets dropped out. That's exactly what's going on when we apply a rate limiting policy. If we say 10 gigs can get in, it's like a cup that's got 300 milliliters or 300 cc's. Once we fill up more than that, it just gets tossed and thrown on the ground. That's exactly what's happening here. Good question there. Any others? Okay. So now we're going to talk about first hop redundancy protocols. Now there's really 3 of them, and pretty much they all do the same thing. There's a Cisco proprietary one called Hot Standby Routing Protocol, which we don't use anymore because it's Cisco proprietary. Then the industry came out with something called Virtual Router Redundancy Protocol, which was specified via RFC 5998, which is a great thing, which we all use. And then Cisco came out with another version to use the same thing called Cisco Gateway Load Balancing Protocol, which is all kinds of cool, but it's Cisco proprietary. So that means we go back to Virtual Router Redundancy Protocol. And realistically speaking, what are these routing protocol things? it would be really, really big, really, really great if we could track an interface. Now with routers, this stuff's easy because the routers have routing protocols and the routers recalculate like the GPS in your car, but not necessarily this way. So let's talk about what we mean. Imagine you've got this environment, and I'm going to draw it out for you because sometimes I feel like whiteboarding these things out in real time is so much easier than trying to just talk to you and show you pre-made slides. So let's go to this environment. In this environment, let's get two routers, router 1, how that happened. Router 2, we've got these two routers. Now, we also have a switch, and everybody's in the same VLAN for right now, so we're just going to say switch. Routers are plugged into the switch. We got a bunch of servers, server 1 or systems, all plugged into this switch. PC 1, PC 2, PC 3, add another PC here. Let's say both of these routers, they're connected anywhere. Heck, this could be the AWS cloud, for example. It could be your internet. It could be Azure. It could be a remote WAN location. It really doesn't matter. Okay, so let's pretend all these PCs. So the PCs, does your PC run OSPF or EIGRP or BGP? No. When you want to leave your current subnet, what does your PC do? It checks its default gateway. So, realistically speaking, on this LAN segment, we can point these PCs to router 2 or to router 1. So let's think about what happens. We point all our PCs to router 2. This link goes away. Every one of our PCs is going here. Nobody's getting anywhere. Now, if we could see if the WAN link goes away, send all the traffic dynamically to router 1, wouldn't that be cool, everybody? So right now we've got two active links. Link 1, link 2, link 1, link 2. Everybody's happy. Traffic's going out 1. That link goes down. I want to know about it. I want this thing to be removed completely. And I want this to take over. So how do we do this? Well, what if we could create a virtual router and this virtual router was connected to both of these devices? So let's say this router, its actual IP address ends in a .1. And this router, a real router, has an IP address that ends in a .2. But what if I made this virtual router .3? And I told all my PCs, this virtual router, that's your default gateway. So I point all my PCs to this virtual router. Now let's say router 2 is the primary. Here's the normal flow right now. Data comes in, goes to router 3, out router 2, back to the cloud. PC 2 goes to the fake router through the cloud. This one goes to the router through the cloud. This one goes to the fake router through the cloud, fake router through the cloud, fake router through the cloud, the virtual router. Everything's good. Now, AT&T's cable gets cut. That's okay. We weren't crazy enough to use a single service provider. We used two. Router 1's on Verizon. AT&T's down. Now the PCs send their data to the virtual router. But this router is done because the link's down. So now it goes this way. Now the traffic goes this way. Now the traffic goes this way. Now the traffic goes this way. Now this link comes back. Poof, this is back up. Virtual router shuts over. And now the traffic goes this way. And it's the same thing. We're directing our traffic. Everything's hitting the virtual router. So hot standby routing protocol is this. Cisco proprietary virtual router redundancy protocol is this. Gateway load balancing protocol is this. What are they? There are three ways to do the same thing. To basically make two routers work together to have a virtual router so it doesn't go down. What do you think this increases? High availability. So that's what these first top protocols are. We can literally track an interface. If this interface goes away, it goes down. If this router goes away, the router dies, guess what? The other virtual router picks up the virtual address. So the point is, this is a first top redundancy protocol. Routers don't need it. Why do routers not normally need it? Hello? 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 Some LSAs, some LSAs, but PCs don't participate in routing protocols. So your PC has a default gateway. Have your default gateway pipe to this, and we're good. Now, what we could do if we wanted to load share, which we can do, is we could potentially, and we can do this, we could have two virtual router addresses. We can have a virtual router 3, and what we can also do if we wanted to get cuckoo here, we could have another virtual router, which we would put at .4. And again, both of these would be virtual routers. And what we could do is we could point half of our users at this router and half of our users at this router. Now, in either case, if this link or this router would occur, both links would be switched to the other router. But we have the ability to send half of our traffic on one link, half of our traffic on another link. And if one of the links or routers goes away, just shift. And by doing that, we're just creating two virtual routers. So one virtual router uses one link. Two virtual routers shares two links. That's how we're doing load sharing across PCs in a high availability context. So when we're dealing with HSRP or the Cisco proprietary one, we've got an active standby because HSRP only allows one to work. One active one standby. Now, there is something called SNMP or Simple Network Management Protocol. And Simple Network Management Protocol realistically is a protocol to manage devices. And this is where we start talking about network monitoring, etc. And what happens is every device has something called a management information base. And I'll explain to you briefly. So there's something called the Simple Network Management Protocol. And the way this works, you're going to have a network management station. And this is a server that basically sends requests to the devices for information. Now, every device has something called an agent on it. An agent is what serves the server. So we've got the network management station that reaches out to the agent that sits on the routers and it asks them for information. Give me information about your CPU. Give me information about your memory. Give me information about your interfaces, etc., etc. So if we want to request information from a device, it's called an SNMP GET. We can also set devices over this Simple Network Management Protocol. And for the people that are your operations people, your SysOps people, they're very good at these kind of things. For architects like me, this is a totally different career and a totally different world where we tend not to be there. But Simple Network Management Protocol is there. People have got to manage these devices. So what happens is each device has something called a MIB, which is called the Management Information Base. And it's basically a little database or a store that has key variables that tells the manager exactly what's going on. Now, let's do this. Let's walk through the way that we would do certain things on the cloud. So how do you, let me find my EVENG server, and then we'll come back to it in a minute. Bear with me. Okay. So a couple of things that I wanted to show you. What we do, the way we get our operating systems to a router is typically via TFTP, etc. So what we would do is we'd tell it copy, we would tell it the TFTP, and then we give it a name or the address, let's say 1.2.3.4, and then we would tell it what we find on the TFTP server to flash. We'd give it a location, and then we'd hit enter. I don't want to do that because we don't have a TFTP server 1, 2, 3, 4. But the TFTP server is where we're going to pull our information. So we talked about a few things. We showed you how to do a few commands. We're actually at the point now where we can actually start to get into some architecture kind of stuff and explain some of these things, which I'd like to do. But before we do that, it might actually be worth, what's the word I'm actually looking for? Seeing if anybody has any questions. Does anybody have any questions, Chris, before we go to the next section and start doing some architecture work?
Yes, we've got some questions.
Hold on one second. Let me go find StreamYard. Rishab Jain. OSPF calculates the path based upon the bandwidth of each link. So with OSPF, realistically speaking, depending upon the bandwidth, just specifies the cost. Now, ever since Gigabit Ethernet came out, all the costs were one. So what you're going to have to do under OSPF is you're going to have to set something called the reference bandwidth. And by doing that, you can specify the link speed, which will specify the link cost. Meaning, if I've got a path that includes 100 gigs that's 5 routers away, the cost of that is less than a path that's 1 gig that's 1 router away. Why? Because I can send so much data. So OSPF, or Open Shortest Path First, is going to calculate the best path, which is going to be the shortest distance in terms of bandwidth or cost to reach the destination. It's not going to be router hops. It's going to be the path that gives you the most bandwidth and throughput. Good question there, Rishab Jain. Excellent question, actually. Chris, if you want to bring in the next one. When connectivity goes down, what backup is needed so voice over IP calls won't get rejected? It depends on how you do it. If you've got 2 sets of WANs, one goes down, it doesn't matter. Your voice over IP is still good. If you've got a server locally, that's a call manager that syncs up with a voice over IP server in a remote location, and it goes down, again, you're good because you're survivable. So the key for any high availability is 2 things. Never, ever, ever have a single one thing, and never leverage a single provider. So whether that means if you're going to WAN, you're not going to build all your WAN on AT&T or Vodafone or Verizon. You must use 2 service providers. Must. If you're connected to the cloud, you must use 2 clouds. Same way we've always used 2 service providers. So the key is this: more than 1 servers, doing the call managers, more than 1 path, and good routing that makes sure that your connectivity never goes down. And then you won't have to worry about this. Voice over IP does best when your servers are actually in the same facility as where your users are. So if you stick your servers in your campus and your campus WAN goes down, guess what? You never have these problems. So I generally like to put my call manager servers, at least the majority of them, in the main campus. But good question. What other questions are here, Chris? Angelo, for MPLS networks, absolutely. We've got our own form of QoS, the degree of service, the fragment offset. Oh, absolutely. We've got QoS service, quality of service at layer 2, layer 3, MPLS, all of it, because it's that important. Good question there, Angelo. Margin, this isn't really a load balancer. A load balancer, figure is a server with some hardware that just goes server 1, server 2, server 3, server 4. Now, we can load balance via OSPF, via equal cost routes. We could load balance by telling, or traffic engineer by telling BGP to leak a more specific subnet over one link versus another. We could load balance with policy routing that looks at the source address and goes somewhere else. So I wouldn't call it a load balancer. I would consider a load balancer to be a device that just shares the load between routers and firewalls and servers. This to me would be a first hop redundancy protocol, but I guess it does do some form of load balancing, but no, it's not considered a load balancer. In fact, load balancers aren't even considered networking. Networking and networking people are basically routers and switches, and that's it. Good question there, Marcia. Sarah Ahmed, what's a TFTP server for? So typically we would take copy running -config to TFTP, which would take the configurations on the router and back them up to a TFTP server. Now, when we need to update the operating system, we often use a TFTP server. Copy TFTP to flash, and that's how we pull down the operating systems. TFTP, Sarah, is also used by if you've got a cable box in your home. When your power goes out, the cable box or your satellite box reaches out to your satellite provider, pulls a configuration which determines what channels you're allowed to. TFTP is widely used for that as well. Great question there. Mike I, where do you use a spine and leaf architecture? I've not used one in 25 years, and every spine and leaf architecture I've ever seen, I picked it up, ripped it out, and replaced it with a core distribution and access layer. So I don't use spine and leaf architectures ever. What is the spine and leaf architecture? Where basically you've got your core routers and everything plugs directly into those, which means you've got no scalability, my guy, which means that if you've got a problem and one of the switches or a bunch of servers keep rebooting themselves, they can take down your entire network. So where do you use a spine and leaf architecture? For a mom and pop shop that's got 5 routers and switches and never anywhere else again. So you don't use core, big, strong routers. And the function of the core is high performance. Then you've got a distribution layer, which feeds in the access layer into the core. And if there's a problem with the access, anything, and it hits the distribution layer blocks it from hitting to the core. So when you do a spine and leaf, it's basically you put everything all in a single basket, and you've lost all your scalability, you lose all your availability, you lose all the performance. So where do you use spine and leaf? I don't. Small businesses might get away with it. The jack of all trades hobbyists would use it, but I've not used it in 25 years. Now, Mike, I have seen a lot of spine and leaf architectures that somebody just thought they could throw their switches and plug them into the core routers. I've removed about 150 spine and leaf architectures because each one of them basically had outages day in and day out because they didn't constrain it. Because what would happen in one of the leafs would just impact the core, and then you don't want that. So you really want it to be that you've got a structure. You've got the main thing that's your high performance. Kind of like the military. You've got a commander-in-chief, right? That commander-in-chief has generals that separate them from the commander-in-chief. Why? The generals are military experts. The president may or may not be. So the president's at the core, the commander-in-chief. They've got generals and admirals and people that advise them. And then those people reach out to the military community. You don't have military people speaking directly to the president, the commander-in-chief. You've got those generals there that are experts. That's why you have them there. Because a military person calls another military person, they speak the same language. Now that general can then translate it to the non-military person, and everybody knows. So same thing, decoupled architecture scale. Why do we take our websites and do a web tier, a database tier, and an application tier? So that each tier grows. Why do we do the same thing with a core distribution and access layer? Because it grows. A spine and leaf is like a one web server environment. We've got the whole lamp stack on a server. Doesn't scale. So I haven't had a use case for a spine and leaf architecture in 25 years, and I've ripped out about 150 of them. But it's a great question there, Mike, and I'm so glad you asked it. Chris, if you want to bring in the next one. Actually, while he's at it, let's draw the two architectures out so that I want him to understand the difference and why, because it's a good question. These are my blank architecture slides that I wanted to get into. So before I do this, let me just, here's the way we design them. Core. And I'm going to show you the difference between a core distribution and access and a collapsed core. and I'll show you where the problem is. So this is your core. All right, so let's just hold this real quick. Let me copy this. We need to do, hold on. So, okay, so this is a spine and leaf. In this particular environment, you've got these servers or computers, whichever you want to call them, are going to be plugged directly into this switch. So these are servers. These servers got it plugged in this switch. Every time one of these servers reboots or gets shut down or gets unplugged, a port goes down. And if it's on a separate subnet, that's going to send recalculations through all of this stuff. Every time a port comes up and down, this whole network's going to know about it. You put 500, 1,000 servers in a couple of switches, and you've got a nightmare. Now, by comparison, if we did it a little different, if we did a core, and off of the core, what we did, which is the way I designed it, we have a distribution layer. And this distribution layer feeds into two different switches in the core. And then the distribution layer then has the access layer plugged in. And the way it works is this. Now, if anything happens on this switch, which is the access, it's going to get filtered by the distribution layer, so the core is not going to see it. So by doing it here, anything that happens here can crush this. By doing it here, anything that happens here will most likely be blocked by here before it hits the core. So by using a 3-tier architecture or a core distribution and access, we can isolate these problems here so the rest of the network doesn't see it. Now, once we go collapse core or spine and leaf like this, anything that happens here can destroy the entire network. So I strongly recommend staying away from the collapse core unless you're dealing with like a house or a mom and pop shop. Now, what happened was these routers and switches got really powerful. And people got sloppy because the routers and switches got really powerful. And here's the thing, because these routers and switches are really possible, you can get away with this idea for a period of time, but it will break. And when it breaks, you're going to have to start all over. So it's best just to design it right in the first place and not have to worry about it. So it's funny you actually got to the thing that I was going to refer to. So what does your basic LAN architecture look like? Your basic LAN architecture looks like this. Switch. Switch. And our switches, what do we have? VLANs, right? VLAN. So let's make sure we can find our text. Let's give our text another color. Okay. So we've got a switch. So now we've got this cable between the switches. And we want to carry multiple VLANs. Okay. Let's say VLAN 1, 2, 3, 4. Carry these VLANs over. We've got them on both sides. Now, both switches are in the same building, but they're separated by a single piece of fiber. So I want to get all 4 VLANs across this single wire. What is that special kind of port that enables me to put VLAN 1, VLAN 2, VLAN 3, and VLAN 4 all on a single wire? What's this called? What is that special port that has multiple VLANs? What are they? In the chat box, please. Do 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 bum ba da 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 bum ba bum bum bum. Bingo! Trunk port. Angela, you got it. It's a trunk port that enables us to push multiple VLANs all on a single port. Fantastic. Fantastic. You did it. You got it. All kinds of happy. You did it. Good, 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 good job. So super exciting stuff. You guys got it. You put a trunk port. Good job. Oh, I'm loving it. You guys are getting it. It's trunking. So the trunk port enables you to capture multiple VLANs. So let's talk about core access distribution again. Hey, you guys are going to get it by the end of this session. Core access distribution. Let's go back and steal some of my stuff so we don't have to do it again. Now let's think about this. Let's talk about why this core access distribution is so good. So now we do this core access distribution. These are all layer 3 links. So let's make sure that we make this really survivable. Real strong. Now, if this was OSPF, does anybody remember the name of this special area that has the most knowledge of our routing? Which is the core of OSPF as our primary interior gateway protocol. What's that area called? That's the core or the center of the network that's designed for the high performance routing that needs all those links data advertisements. What is it called in the chat box? Do 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 boop. Woohoo! Area 0. LM, Area 0, Angelo, Area 0, Anya, Area 0, and Area 0, Mike and Mark. Woohoo! You guys are getting it. So high-speed routing, critical ports, all the routing here. Area 0. So these devices are fast. Now, what do we know about all the routers in Area 0? Every network change that they see happens. Everything happens. So these have to be big routers, strong routers. The routers that walk around look like Arnold Schwarzenegger in his prime. Big, strong routers, big cables, powerful devices. Now, well, here's what we need to do. These are your biggest, baddest, most expensive high-performance routers. Now, by decoupling this, these distribution routers, they should be layer 3 devices, high-performance switches, layer 3 switches, routers. Why? Why are these layer 3? Now, do routers forward broadcasts out of their segment? No. Remember, that's why for that DHCP discover, give me an IP address. We had to have that helper address called the DHCP relay. So we're doing that. Now with layer 3, routers don't forward broadcast. Can I do an access control list on a router that says only this traffic can go in a certain direction? Yes. Can I put QoS on my router to make sure the bad traffic never gets to the core in the first place? Yes. Can't do this as much the same way with the collapsed core, but I can here. So now I can run QoS. I can run encryption on my routing. I have more packet filters, more ACLs, more everything. Now, by doing it this way, if it's a layer 3 link, I can make sure the changes that happen here aren't seen in the same way. I can hide it. I can route summarize. Now I've got a set of these little mini access switches. I can plug a couple of these little devices into this device. And you want to see how cool I can get with regards to availability? I'm going to show you. In this particular environment, it's not supposed to go this way. So let's drag all this stuff over. Now let's pretend this is a high availability environment. Say I'm dealing with stock traders. Stock trader. Let's say I've got 4 stock traders here. We're going to have a lot more. But I want you to see how cool we can get and how high availability we can do with this core access distribution layer. So we've got 4 stock traders. Here's how we do it. This is high availability, high performance systems. What I'm going to show you right now, very few people in the world will ever get to experience in their life, and very few people will get to do this. So this will make any of you that are taking this free training already better than 2/3 of the population that are working in networking for years of experience. So let's talk about this. You've got traders. What do traders do? They buy stock and trade it. They sell it. Companies make a lot of money on this. Imagine this. These 4 traders, trader A sits next to B, sits next to stock trader B. Make these boxes a little bigger. And I want you to fully appreciate how high availability we can get with this. So this is going to be stock trader C. We'll show you why we love this approach. And I use this approach for everywhere. And let's say this is stock trader D. Now they're all sitting at the same desk. Stock trader A is sitting next to B. So if we send stock trader A to this switch, and then we send stock trader B to this switch, and then we send stock trader C to this switch, and then we send stock trader D to this switch. I want you to think what we did. If this switch dies, big problem, right? Stock trader A can just walk over to stock trader B's desk who's next to him and say, process my trade. Stock trader C can do the same thing for D. Now this router comes back on, and this one goes away. The traders can go next to them. So by doing it this way, this switch fails, this distribution thing is going to fix it. We don't even have to see it. It doesn't have to affect the core. This thing fails, we don't have to see it. So by decompartmentalizing, everybody can see it. We can really lock these systems down. Now, Cisco loves to teach this spine and leaf or collapsed core. I hate it. But because of this, it brings us back into this situation. So now we're here. Imagine if this is a layer 2 switch instead of a layer 3, which is typically what you see in these collapsed core. Anything that happens here will literally affect every one of these devices. Now, how's that going to scale? It can't. Even if this is a layer 3 device, this guy gets a worm. It hits this thing. Chances are this thing's not designed to be a big, strong distribution layer to protect the core. Again, it goes down. So I tend not to like this. So let's talk about what a small office is going to look like in reality. Well, here's what it's going to look like. In a small office, architecturally speaking, you're going to have something you're going to connect to. And it's either going to be AWS, Azure, Google, or a data center. It doesn't matter. It's all the same. All these clouds are nothing more than a data center that's been virtualized. That's all it is. So what is your small office, home office? That's what SOHO means. Well, you typically have a what do you call it? Got an internet connection. And your internet connection, you typically have a firewall that also does VPNs. So we can call it FW/VPN/router. Behind that, these little devices typically have, the firewall typically has a couple of switch ports on them. And maybe one of these switch ports goes to your IP phone. Maybe you've got an IP phone. And maybe over here, you've got Cindy on her computer. Cindy does all kinds of computer stuff. You have no idea. So we've got Cindy on her computer. And then Cindy's father's on his computer. So you've got Mike over here. And we got my wife over here that's doing stuff, doing some accounting and things like that. So we've got Lisa. So realistically speaking, this is the kind of thing that you would typically see in a small office or home office. Now, if the small office and home office mattered, they wouldn't just have this one internet connection. They would have a backup internet connection across a second service provider. Why can't you get two AT&T connections? Well, if the AT&T fiber gets cut, you're good. But if the AT&T network goes down, you're not so good. So let's talk about WAN architectures. Pretty much simple stuff. WAN architectures are going to be one of two kinds of things in today's world, and it's all going to be the same. You're either going to get your router over here, router. You're going to have a router on the end, and it could be one of two things. You could be buying a wire across the network. That's called a pseudo wire. You could be buying a real wire, or this could be Ethernet over MPLS. And guess what? It's immaterial to you. All you're going to get is a gigabit Ethernet connection on one side, or a 10 gig or 100 gig, and a gigabit Ethernet connection on the other side, and that's all that matters. It doesn't matter which technologies you're using. The alternative, which is what you typically see in the cloud, is the same darn thing. How does it work? This is the basis of a direct connection, which you'll see with AWS or what they have in Google or Azure. They're similar. What happens? You've got your router. Your router gets, you buy a WAN connection or gig ETH to something that's called a point of presence or a direct connection location. Inside of that, you've got your device. This is called customer edge. Now, inside of that location, you've typically got your cloud router. Call it AWS, doesn't matter. It could be Azure, it could be Google. You ask them to run a wire. It's called the cross connect between yours and theirs. And then AWS will just backhaul your connection. And guess what? If you've got any of these kind of connections to your cloud providers, all it is the same Ethernet WAN. You get a point to your location in the end, and then you just plug in the AWS switch. All of this is the same. Let's say it's Metro Ethernet. Guess what? It doesn't matter. Here you got a big, tall building. Who's connecting to another building? What do you think you got under the ground? Fiber. How else does this often work, Metro Ethernet? You go to a phone switch over here, which is buried underground, or another switch which is buried under the ground. You connect to this switch. That switch connects you to another switch, which connects you to your far-end building. Does this look just like that AWS direct connection or Azure direct connection or ExpressJet that I just showed you, or the direct interconnect that Google just does in the previous slide? It's identical. Connect to a switch, you connect it to another switch. So what are you really seeing? This is the same stuff that we've had for the last 30 years. What's a point-to-point WAN look like? I'll show you. Got a router over here. Router over here. Router over here. We connect the link between them. This is a point-to-point WAN. How many IP addresses? Everybody, how many IP addresses do we need for this WAN? And what is the appropriate subnet mask for this WAN? For this one address here and one address here. What is the perfect subnet mask? Slash what? Slash what to give me 2 usable addresses, but a total of 4 addresses per subnet? Help me, help me, help me. What could it be? What could it be? What could it be, everybody? Well, Jim, we need more than one address because we need one for each side. Angelo, fantastic. We need 2 addresses /30. Sharon J, fantastic, /30. Sarah Ahmed, /30. Tom Artheus, /30. Woohoo! Mike, /30. Jim Weaver, /30. Brian McCool. I'm loving it. You guys got it. A /30. Let's look at the other architecture. This is called hub and spoke. If any of you have ever been to an airport, you know hub and spoke architectures. I'll show you the airplane thing. I'm going to go see Ivadoikya first. Ivadoikya is over here. I want to go visit Ivadoikya over there in Hungary. So I'm in my Palm Beach airport. I'm over here. What do? I go to PBI. This is my local airport, Palm Beach International. I go over here. I have to connect to a hub. A hub is Atlanta. I go to Atlanta. I go straight from Atlanta to Hungary. That's a hub and spoke environment. But let's show it in the network world. Let's just say that Atlanta is our hub. And we've got a site in London. Lagos. Cape Town. Dubai. New York. San Francisco. And I was listening to Ziggy Barley singing Beach in Hawaii this morning while I was doing some yoga. So we'll say Hawaii. So, and I know that's a country or a state, not a city. So, where everything else is a city. So I probably should have picked a city, but I couldn't think of it. And I was thinking of Ziggy Marley's Beach in Hawaii song, which I absolutely love. So this is Hub and Spoke. Now, how does this work? Atlanta is the center of everything. London sends its route to Atlanta, which sends it to Dubai. New York sends its routes to Atlanta, to Dubai. San Francisco sends it to Atlanta. Everybody can talk to everybody through Atlanta. This is called the hub and spoke. What do we know about this? Highly, highly, highly efficient because we only need one set of connections. Now, what's the weakness? Atlanta. If Atlanta goes away, nobody can talk to anybody. So if we're going to do hub and spokes, what do we need? We need two hubs. Or if we're using a single hub, this data center needs to be real high availability. Two power companies, two sets of generators, two sets of backup generators, two sets of UPSs, air conditioners, redundant air conditioners. You see what I'm talking about? When it matters, we can't have a power failure take down our environment. So these are the kind of things that we're talking about. So these are the ways we're going to do this. Now, what if we needed better? What if we needed super rapid communication? Guess what? No big deal. We can do this. Now, mind you, we're not going to do too many because we're going to get into this math problem that's called n times n minus 1 divided by 2. And it's going to get real ugly, and I'll show you. So right over here, we've got 4 devices. So to go full mesh, everybody's connected to everybody. And in IBGP, you would be dealing with this. With VPC peering, you would be dealing with this because IBGP and VPC peering in the cloud is non-transitive unless you do something to create rules to break those rules to make them transitive. So this is full mesh. Everybody's got a connection to everybody. Now, let's think about this. This router is one hop from this router. This router is one hop from this router, one hop from this router, one hop from this router. Everybody can reach everybody in a hub. Now, this is really efficient. But look at that number of connections. I've got 6 here. Now, I want you to think about this. Hopefully, some of you guys are good at math. So here's the formula with full mesh, the number of connections. N times n minus 1 divided by 2. So imagine you have 100 routers. So let's do it. Let's do the math for 100 routers. So 100 times 99, 100 times 99 divided by 2. If I've got 100 routers, I'm going to need 4,950 connections. Ugh. So not good, huh? Hub and spoke, we need 100 connections. Fully mesh, we need 4,950. So what you can see is this grows exponentially because the formula is n times n minus 1 divided by 2. So this does not scale. So what are we really doing? Well, Let's show you what practicality is. How do you really design the perfect architecture? You combine them. So let's go back to our pretty hub and spoke. So let's do this. Let's call it something different. Let's call this hybrid. So let's look at places where people really need to talk to each other and go play a lot. So we know that there's a huge connection between London and Dubai. We know there is, because we see a lot of people. We also see that people are constantly talking to each other between New York and San Francisco. And we've noticed that our folks in Lagos, Nigeria, seem to be spending a lot of time talking to our folks in Cape Town, Africa. So we draw a connection between them. And what does this do? This means if Lagos, Nigeria goes away, Lagos, Nigeria can go through South Africa and still reach us. But the two cities in Africa the two cities in Africa can reach each other across two countries as well with a relatively low latency because they're in the same place. London, Dubai get to talk to each other frequently. New York and San Francisco speak to each other frequently. So this is kind of a hybrid approach. Why? Better redundancy and better performance when we need it. So I live in Palm Beach. I can fly direct to New York because there's so many people going between New York and Palm Beach, even though New York isn't my home. So keep that in the back of mind. Now, if we were talking about VPNs, what would that be? Well, there's lots of VPNs. So, we used to have this. This was the first cloud I worked on. And all of these were VPNs. So I just want you to all to know how old the cloud is. Cloud is old. This was what I had. And this is what I grew up with. And if you people know networking, then you truly know the cloud. I'll show you why. This was the first cloud I worked with. This was called Frame Relay. And how did this work? We would get a connection to the cloud, like a T1, for example, or a 56K lease line, what have you. It didn't matter. And then on the cloud provider would create this virtual connection between us. It wasn't real. So that was the first VPN. That's called Frame Relay. Then we did ATM, which was the same thing. After this, what we did is we filled this up with BGP. We did multi-protocol BGP. And what we decided to do was keep our customers separate. And how do we keep our customers separate? With multi-protocol BGP, we came up with this concept of a virtual router. And basically, we had these virtual routing interfaces and virtual routes that we'd push through. Now, the underlying technology that made this work was MPLS, but it was no big deal. And then after this, you know what we came up with? We came up with VPLS, which is based on the Martini draft from Luca Martini over at really smart guy over at Juniper Networks. What was VPLS? Well, we decided, quite frankly, to do the following: to just basically build a wire over. We had an MPLS network, and we were submitting wire signals, and that way we could have point to multi-point architectures. Like we could have another router over here, and what we could do is we could just, literally speaking, create connections through the cloud to each other. That's not working so well. Wait, I think I got to do it that way. And that's what we were doing. We're effectively sending things, but they were all VPNs. But what does your normal VPN look like in today's world? Well, quite frankly, it looks like this. It looks like the internet, and because it's the internet, we don't know what it looks like. That's why it's a cloud. A cloud means you just can't see it. It's hidden from you. So let's say here is the internet. Now we've got the internet. Over the internet, we've got a router on one side. Guess what? We'll put a router on the other side. We send some encrypted data through the internet, and it looks just like a wire. That's a VPN. Now, maybe if you guys want, I'll build a GRE tunnel. So let's think about a few more architectures while we're at it. All right, let's say a cloud architecture. Okay, now we're dealing with the cloud. No big deal. Now, what's this look like? Okay, let's think about it. Now we've got our place. We've got our data center. We've got a router. We've got another router. Okay. How do these things work? Pretty simple. No big deal. Our two routers then connect to two different direct connection locations. See? Actually, I should call this point of presence, but really speaking, it's just a data center that's owned by somebody, but let's call them a POP or direct connection location, whatever. Now you're in the POP. You run a wire back to the cloud. Let's say this is AWS, doesn't matter. Could be Azure, who cares? All the same. Only the names have changed, like that song, Meet the New Boss. Same as the old boss. It's the same old 20 to 40-year-old data center technology, which we're using. Now you got your cloud. Layer 2 link back to your VPC. Same thing. None of it's different. It's all the same. It's just the name has changed. And if you know these technologies at the baseline, guess what? It's all simple. So when you're on the cloud, you've got what's called the VPC. Now, okay, you're on the cloud. We got our virtual private cloud. Let's have fun with it. Let's draw ourselves a VPC. So here we go. Now we're on the cloud. What are we going to do in our VPC? Okay, we've got our virtual private data center, VPC. Let's change this to black because let's see if we can do this. Let's change this to black. Okay, now let's get rid of all this fill in here. I didn't mean to do that. How do we do this? Shape fill. We want to get this to 0. Just blacking it. Okay, so we've got our VPC. So let's think about this. What's in a cloud? We got an internet gateway, right? What's that do? It's a router that takes us to the internet. Okay, no big deal. So the internet gateway is going to need what? A public IP address. Now, when we get past the internet gateway, we're going to have a firewall. But let's just assume we're not dealing with any firewalls and VPN concentrators. We're typically going to have what? A load balancer of some kind? Which is going to have a public IP address on it, which is going to connect ourselves to an internet gateway. Behind the load balancer, we're going to have what? Web servers? Okay, web servers. Heck, let's have another load balancer. Have some app servers. Behind that, we'll have some kind of a queue. On the way to our database, let's say queue. And I know my spelling is trying to fit in here. Now we've got a database. Now people say, how do I manage this stuff? Oh my God, how am I going to manage this? What do I need? Some kind of crazy thing called the Bastion host? Of course not. How do we manage this? And because, you know, some of the cloud providers have made up this ridiculous thing called the Bastion host, which basically teaches you how to avoid all your firewalls, your IDS, IPS systems. It's basically like hanging a sign on your door that says, please hack me. So now let's look at what this is like. We've got our data center over here, DC. Now we've got our virtual router at the cloud provider. And whether this is a direct connection or a VPN tunnel, guess what? We've got full connectivity directly to the cloud through this connection. And we can manage our load balancers, our servers, all this stuff directly through this. So why am I talking about this cloud thing? I want you to see the cloud, which is the future, the network, which is the past and present. It's the same thing. It's all the same thing. So why can't people get hired as cloud architects? They don't know the network and the data center, which means they don't know the cloud. They just know the name of the service and how to configure it. So, these things are really easy. So let's talk a little bit about server virtualization, because all of you guys working in networking somewhere along the line are going to be working on the cloud. So what is server virtualization? Quite frankly, it is the basis of all cloud computing. Quite frankly, server virtualization is 50-year-old technology from IBM that was used to virtualize mainframes. That's how old it is. Cisco came out with the VLAN or virtualization, which was virtualization 30 plus years ago. Then Cisco came out with the concept of a private VLAN, which was a VLAN where people inside the VLAN couldn't talk to each other. Wait, in 2021, don't they call that a container, where you've got multiply isolated things on the same operating system? So now it's all the same 30, 40-year-old tech now that you know what it is and where it comes from. So what is server virtualization? Quite frankly, it's a VLAN equivalent of a server. So what is a virtual LAN? Well, a virtual LAN is when you take a switch, like my happy switch that I keep next to my desk, and you take some of the ports and you chop it into multiple logical switches. So what is server virtualization? Take a server, chop it up into logical servers. Now, how do we do that? Well, I'm not the best graphics artist here, but I drew this for you. So here's what we do. We take our server, we smack something called a hypervisor on it, something like VMware ESXi or KVM on Linux or QEMU, and we create a virtual machine. It's got our own operating system and applications. Now, that EVE-NG server that I'm using, each one of those little routers is its own virtual machine. So I've got a server sitting there with a VMware ESXi hypervisor that's then doing nested hypervirtualization with KVM and Linux hypervisors. And I've created this. That's how my server is running. But when you go to the cloud and you get a virtual machine on the cloud, this is it. And it's the same thing if it's in your data center as VMware ESXi. It's the same thing with Amazon's creative naming of Elastic Compute Cloud. It's the same thing with Google's creative naming of Compute Engine Instance. And Azure calls it a virtual machine. But guess what? It's the same technology. So while we're at it and talking architectural concepts, this is a type 1 hypervisor. This is what all server virtualization is. But maybe you decided you had a Windows notebook and somebody decided you wanted to learn Linux and you don't want to make Linux your primary operating system. You decided to make Linux run in a virtual machine. So desktop hypervirtualization, your notebook. You're running a Mac and you need to do something in Windows. You've got your physical operating system, and then you've got your host op, and then you've got your hypervisor, and then your things, which is why if you've ever made a virtual machine on one of your Macs, it doesn't work that well. Why? Because it's type 2 hypervisors. Server virtualization, awesome. Non-server virtualization, not so awesome. So our type 2 hypervisors, not so great. So while we're at it, let's talk about what a container is, because it's another form of virtualization. Private VLAN, Cisco 2000. Containers, Kubernetes, 2010 approximately. Same thing. Physical hardware, operating system, container engine. Now you got your containers. Now look, your container is just your application and libraries. It's not a whole operating system. So this is fast and light and efficient. What time is it? So what is a private cloud? Take a data center, install. Okay, we'll build a private cloud real fast. We've got our normal data center. What does our normal data center have? Let's build it up real fast. Bear with me a second. So we've got this. In our data center, we've got this. Let's replace this with server. We're all servers. We've got thousands of servers plugging into our switches. You can see we're pointing our servers to these switches. Our servers are connected to the system. Now in this environment, all these servers, if we install a cloud cert on them, like OpenStack or Nutanix, and these clouds are fantastic, OpenStack or Nutanix, what are we now doing? We're now enabling these servers to all be virtualized. And now when I create a virtual machine, we enable the virtual machine created any of these pools of servers. I need a load balancer. It becomes a virtual device that's literally running on one of these servers. It's the same thing as the data center was before, except instead of having physical machines, or now VMware ESXi virtual machines, we've got virtual machines on our cloud, which is Nutanix or OpenStack. Same thing. Oh, wait. Now I went to AWS. Okay. Now I got the same data center as before. It's the same thing. But now AWS changed the name of these servers to EC2. Oh, wait. I went to Google. Now it's called Compute Engine. It's the same. All of it's identical. It's the same 30, 40-year-old data center technology. Why is this interesting? Why? Because it's a new name of the same thing. So if you strip off all these stupid names, Elastic Compute Cloud, Compute Engine, and you know it's a virtual machine, you now know that when you're in the data center, AWS, Azure, Google, even Deutsche home, or Jazz is home running a VMware ESXi server, you can build your same cloud, and it's all the same. So now you know. Nothing fancy, nothing spooky here. It's all just the same old school technology. So while we're at it, let's talk about a few kinds of definitions. I hate these terms. I think they are horrible. But in case you see them on exam, I don't recommend using these terms with customers. They will laugh at you. But the cloud providers have made up these terms. They all use them. And as a network engineer, systems admin, network architect, cloud engineer, cloud architect, solution architect, you got to know them. So we're going to talk about these terms. Infrastructure as a service. Infrastructure service basically means you're using virtualized infrastructure in the cloud. So virtual machine in the data center, virtual machine in the cloud, that's called infrastructure as a service. It is the most common form of cloud computing. It is the most appropriate, and it gives you the most flexibility. The next type of service on the cloud is something called software as a service. And as software as a service is, the cloud-based provider basically gives you software. And wherever it's at, you don't know much of anything where it's at. It could be on virtual machines. You don't know. The underlying technology is hidden from you. So basically, it's your code. So, or it's basically just somebody's software. It's all licensed and paid in. Now, with this software as a service, do you think you have any control over it? No. No. Do you think you can do layer 2 access lists? No. Do you think you can do any packet filtering? No. Do you think you've got any next generation firewalls that you can do? No. Do you think you have any control over anything with the software as a service? No. So what is software as a service good for? Speed and flexibility and agility. I use software as a service. I use the content management service from software as a service. And when AWS goes down, they go down too, because they're on AWS in 2 regions, in 2 availability zones. When AWS goes down, because they're only using a single cloud, my systems go down too, because it's software as a service. And every problem that they have, I have. Big business, infrastructure as a service. I'm making my own. Software as a service, I'm placing my bet and trust in somebody else. Now let's talk about platform of a service. Platform as a service is a development platform that's based out of pre-built service. So basically you're getting a virtual machine and container, but you have no control over it. Realistically speaking, when you start just rolling out your code on those kind of things, that's there. Single point of failure. You can't control your security. And if you start redesigning your applications to work on platform as a service and the cloud provider kicks you out like they have, you were dead. You're done. So platform as a service, very agile. But cloud provider raises your rates. You can't do anything about it. You are handcuffed. You are now a prisoner. So the best architectures probably involve all 3. Infrastructure as a service, it's your same data center. Platform as a service, basically, it's just pre-made for you. Give them your code and just hope it works. Hope everything's perfect. Can you control the firewalls? No. Can you control the QoS? No. Can you control the capacity? No. None of it. You lose it all. But organizations like it because it's simple. But, you lose all control with these elements too. So kind of keep that in the back of your mind. Okay. All right. So I think we've talked about a lot of concepts. Let's open it up for some questions. Tomorrow we can do some lab stuff. We covered a lot of content. So let's see who has what kind of questions for me. And let me know. And then pop in the questions if you have any.
So we don't have any questions just yet. As soon as they come in, I'll make sure to put them on the screen.
Okay, so ask some questions. And then tomorrow what we'll do is we'll have a nice fun lab where I'll put some pieces together. Maybe if you want to even do a little bit of BGP. But please feel free to ask your questions. I want to make sure that we take good care of everyone. I want everybody to have a very good learning experience because I want everybody to have the best career possible. Marjan, thank you so much. Super appreciative. I love virtualization too. Roger Daltrey, yeah, some good music there from The Who. Meet the new boss. Marjan, thank you. And yes, thank you, Chris, but also Eva Doikia, Jazz, or anybody else that's got a blue wrench, we're super grateful. Sharon J, actually, the vendors make up their names I think it's for two reasons. So when I used to practice medicine, these pharma reps would come in and they'd have these cool names, Lipitor or Ally. What would happen was companies make up these names because it's really hard to sound like you invented the really exciting elastic compute cloud when IBM invented it in the 1970s. So I think it's, how do you take something old and make it feel new and charge 10 times more than it used to cost? You make up some names and it makes you sound cool. So the vendors, if you notice, the cloud vendors have been using some funny things. A cloud provider, for example, talked about having an outage which took down half of the country because they had a power outage in the data center. No, I don't know how you have a power outage in the data center because you typically have two power companies, two sets of generators, backup generators, UPSs. So I don't know. But we're hearing these cloud providers often make up terms to try and make the old 30, 40, 50-year-old thing sound so new and exciting. And I love these cloud providers. Their services are great. The problem is we get all these people, they're certified, and all they've learned is the name of the service and how to configure it. They don't know how any of it works. They're unemployable. And it's all based on these name vendors making complicated names. So, in medicine, let's say I've got a drug, an ACE inhibitor and a beta blocker, two drugs that are off patent that are 40 years old that are each $2 each for me to prescribe. We then have a drug company that puts the two of those drugs together and they get a patent and they call it a new drug. Now, the new drug is $800 a month. And insurance is paying for it because they just changed the name. And it's now a proprietary patented combination when it's two $2 drugs, now $800. So it's that. It's very hard to charge a lot of money for an old technology, but it's a lot easier to charge a lot for something that sounds cool, that's exciting. And Angela, I hate to give you the answer, it depends. It depends on the size of the routers. It depends on what you need. If you need to use, for example, if you're running MPLS, you're going to have to essentially use this poorly architected single area network because you're looking for certain information and different types of LSAs to carry the information. If you're dealing with more enterprisey functions, the key is to have your core in area 0 and to create areas, whether they be not so stubby areas or stub areas or totally stubby areas, so you can limit your LSAs. That's that kind of thing is a CCIE scaling strategy kind of thing, like they barely covered in the CCIE program. I didn't learn that until I passed my CCIE and had a couple of years of work. Maybe one day we'll do an 8-hour webinar on scaling OSPF because I think it would be kind of fun. But it would take a full 8 hours to do it. But that doesn't mean we won't do it someday. Chris, you want to bring in the next one? In OSPF, you cannot create a second area 0. You must have only a single area 0. If you were to buy another company that had another area 0, because the rules state you have OSPF area 0s, you'd have to create some kind of a virtual link to connect them. But you would never, ever, ever desire to create a second area 0, only one. When are we doing a DevOps course? Rahul Sharma, I am an architect, and DevOps is about automating software release cycles. So I don't plan on doing a DevOps course anytime soon because I train cloud architects, and that's what I do, and they're system designers. And I train people for one career, and maybe networking as well, but not DevOps. It's a totally different career. So I don't plan on doing anything in DevOps. Nike, thank you so much for the clarity. Nike, I'm always happy to do so. Sharon, love it. I can appreciate that so much. Thank you so much. Thank you, Mike. I appreciate the tips for the new song. Marjan, it's good to see you. Love the smiley face, by the way. What about using Packet Tracer for the lab? It appears simpler. Anya, if you've got Packet Tracer, go use it. It's a great product. But I like EVENG because I can test Cisco stuff, Palo Alto firewalls, Fortinet firewalls. I can run my IDS, IPS systems. I can generate it and connect it to my cloud. And so, Anya, I use the paid version of EVENG just because it's so robust. But Packet Tracer is great. It's fantastic. You could also go to eBay and buy a CCNA rack for $200, use it, and then resell it on eBay when you're done. That would be fine too. But I like EVENG because lots of organizations, including big ones, use it to test different things. And I've got students and I've got a school, so people are constantly looking to do new stuff, and I want to make sure that I can make my students do anything they want to use to learn. Williams. Williams, no, we don't give away our internal slides. There's something, we give a lot away for free, but we don't give away our intellectual property. Angela, OSPF doesn't really have anything to do with latency. OSPF has to do with finding the path. There's really no latency component into it until you're dealing with MPLS, and that's very specialized. And again, it's giving you latency information, but it's not using it to drop packets. Chris, you can go to the next one. Abigail Marks, I'm so happy to see you here. CCNA. Danica, okay, all of you. You can type hashtag CCNA in the meantime. Mike, you should be the stunt double for Christopher Maloney on Law and Order. I'll have to see that show to see what you mean. I honestly don't have a lot of time to watch TV. I wish I did. Thank you so much, Ivadaikia. I'm super grateful for Chris and everything he does, as well as Leo, but also all of you guys out there. I'm so thrilled that you're here. And Ivadaikia and one of those amazing blue wrenches. Thank you so much for all your help with everything you do. You do so much to make us, this family, this Go Cloud Careers family, and all the students so happy. I'm so grateful to you, Ivadaikia. Maybe.
Sorry about that. I just gotta. As soon as I saw that, I was like, "Yeah, he could."
I like that.
Yeah. Oh, that's pretty funny.
It really is.
Yep. Oh.
Appreciate that, Sharon. Ava Dike, thank you so much. I don't even know how to say thank you to you. Angelo, you're so welcome for this session, and we're so happy to spend some time sharing things. Frank, CCNA, fantastic. Mohammed, so thankful you're here. Marjan, so thankful you're here. Nick B, thank you. Mike, Chris, and the Blue Wrenches. Yes, thank you, Blue Wrenches. So appreciative of all of you. If you can type CCNA. Sarah Ahmed, thanks, Danica. I love that. Single point of knowledge. Thank you so much. We try so. And by the way, Chris keeps everything organized and working. I can't thank Chris enough. And he is the point of organization. Alexander, CCNA, Efharisto, Yasu. Sarah, so good to see you. Nike, CCNA. Finney, so good to see you. LM, CCNA. Ivadaikia, we love having you here. Tom Artheus, thank you so much. And yes, Chris is doing fantastic.
Yeah, I got to think quick on my feet with Mike. That's
Yeah.
The good thing is that when I saw that comment, I realized I bet Mike probably doesn't know who he is. So I already started looking it up before.
Yeah, Chris really knows me. So I so love to watch TV. I just never have a lot of time for it. So, my idea of TV is when I get to see my wife for about an hour and a half at night, and it's me and our little cat, and we all watch TV together. Whatever it is, I'm just happy to spend the time with her.
I like this one. So Christopher Maloney plays a detective. So you're the networking detective.
Yeah, I'll work with that. You know what? For a little while, I ran around with the sniffer, and I had a manager that called me Sniffer Boy. Networking detective would have been so much better than Sniffer Boy. I like that. I literally ran around with the sniffer, plugging into span ports on switches, trying to find out what kind of traffic existed. It was hilarious in those days. Nikhil, good seeing you. Sharon, good seeing you. Thank you so much, Seven Seers Beamer. I've always been wound a little too tight. Let's put it that way. Sarah Ahmed. Sarah, with that name, shukran. Ben Christopher, Cloud Hired CCNA. Robert Welch, good seeing you. CCNA, Nivajoikia, good seeing you. CCNA. Sharon, thank you so much and Brian, thank you as well. Thank you, Mr. Businessman. Williams, I'm so happy to see you. Mr. Gee, I'm thrilled to see you. And I love that name. I don't know if you're a jiu-jitsu guy or you like to cook with ghee. Angelo, haha, that's good to see you. Carlito Way, I love the movie and I love seeing you here. CCNA. And Network Pro, I'm so happy to see you here again. One day we should talk. I really like having you here. Leo Paredes, thank you so much. Leo is exceptional. Leo was one of my best students, and I had no choice but to hire him. He's now a senior manager of operations, making sure that I do what I can and helping Chris, and we are grateful to have you here, Leo. So in any case, I hope everyone had a wonderful day. Tomorrow, we're going to make it a special day to have some fun to end this on a high note. I promise a special lab or BGP or one of those two things, which you guys tell me whichever you want. Actually, tell me, which do you want tomorrow? BGP or a big lab day? Tell me in the chat box, and I'll make it exactly what you want it to be.
I was going to say, why don't we do both? We can do a BGP session next week or the week after.
Okay. Would you like that? Would you like that?
Oh, there's a lot of BGPs.
Okay, so let's do the BGP tomorrow.
Yeah. Oh, I got one lab. Two labs. It's no comparison to the BGP though.
So why don't we do
here's a good balance. It sounds like BGP and a little lab.
If we have time to do both, we can. I think I can definitely do a BGP one. Or I could do a lab, and then we could do a BGP one again when I get back from my vacation. If you guys want both, tell me both. Otherwise, we'll do BGP tomorrow.
And they have been for 4 or 5, maybe longer, 6 years. They've been helping us promote it.
You see, I don't think we can do both in the same day, and here's the problem. It's going to take us about 3 hours to explain BGP, and it's going to take us 3 to 5 hours to do a BGP lab, which I'm happy to do with you guys.
So 7 Series Beamer makes a good point here. We've got some BGP content out there. I think it's a good opportunity to get more lab content and lab in front of people.
Okay, so why don't we do this? Why don't we do some BGP lab tomorrow, and I'll teach BGP about with everything we're doing along the way.
And we'll always do more.
Yeah, so that's why.
And I'll come back and do more too. So we'll do a BGP hands-on day tomorrow, and then guess what? I'm going to do the BGP instruction, and then we'll configure. Then I'll instruct, then we'll configure. And then, you know what? We'll make sure that we give you guys a big BGP day after we know that you've done the BGP configuration. So instead of this, maybe we'll do a semi-instructional and lab day tomorrow. And then after that, we'll do a 4 or 5 hour BGP thing. Or maybe we'll just do an 8-hour session one day. My team and I will look back and see if we can figure it out. And we can do a full day of heavy BGP and call it like a CCIE lab day. So that's potentially in the works of something we could potentially do at some point in the future as well. But let's do BGP instruction with lab tomorrow, because that's what everybody wants. And then we'll go back and have a heavier BGP day in the future, and or a CCIE job day just for fun. So that's what we can do. So super excited about all these things. So let's work off this. Tomorrow, we're going to be doing lots of cool stuff with BGP and labs. It'll be educational in every way, and then we'll bring it back and we'll have another BGP day. So everybody, let's have some fun. Type hashtag CCNA. Type actually hashtag CCNA and Cloud Architect. I want to see it both, because I want to know we're all having a good time, fun. We'll be doing lots of BGP tomorrow, I can tell you that. So, starting to see all these cloud architects and CCNA, this kind of stuff makes me happy. It means you're all awake, alert, oriented. So have a wonderful night. If you haven't done so, please hit the like button, comment, subscribe. Please tell others about our channel if you have not. We want to work really hard to do the community. That's why we're making sure that we have these courses out there so everyone can get a cloud architect job, a network engineer job, a solution architect job, and network administrator job, and network architect job. All of you, I want you to have the best careers. That's why I do all this. That's why I'm here with you. That's why Chris is here. That's why Leo's here. And that's why my wonderful Blue Wrench students are here helping you, because we want you all to have the best cloud architect, network engineer, network administrator. Let's face it, I just want you having a great tech career. I want you to make your vacation your vocation, and I don't want you to ever work a day in your life, and I want you to get paid well to build your best career. So I'll see you all tomorrow. Have a wonderful night.